No, I don't have any such. It's called the pitch drop scale. Yeah, it's almost a glass. All steps. I know. Yes. Et donc, comme je connais la distribution, il y a qu'un bruit qui va me et c'est pour ça que j'ai commencé par avec une sorte de comme je sais que la dynamique
La probabilité d'observer une réalisation. Je vais un peu pour le moment.
I'm a year after some I have to go.
Parce que ça ressemble à quoi? Cette probabilité-là et la probabilité-là, c'est pas exactement la même. Mais tu vois, le lien entre lui et son c'est que la dérivée, par exemple, de l'un, c'est le même à l'autre, etc. Donc en fait, quand je vérifie que ça égale ça, la plupart des termes vont se simplifier. Les termes vont se simplifier. La seule chose qui va rester, c'est une combinaison de sigma, de dérivée, et tout ça. Et je veux que ça soit. Je fais là. Ça va me donner. Et ensuite, ça, parce que tout ce qui est impair dans le temps, ça va se simplifier. Et ça, si tout se passe bien, c'est l'intégrale de La seule façon que ça te donne une équation différentielle, ça te donne une équation de cinéma, ça va une mobilité totale. Par rapport au temps, ça te donne un chemin. Ça te fixe. Je peux t'envoyer le détail de ce non, 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 c'est pas ça. Non, non, c'est pas très simple. Non, non, parce que là, tu perds. Alors, il y a d'autres méthodes qui sont fortes, c'est simple. Mais là, tu perds l'identité de phase. Tu ne peux pas écrire, c'est pas dit dans cette époque. Parce que tu as une table cosmétique qui prend. Donc, moi, ma façon de contourner, c'est de d'abord dire, ah ben, je fais ça. Je suis sûr que je ne fais pas. Et donc, si ça fait cette forme, ça va me filer le main et ça va pas être. Mais il y a d'autres. Je peux t'envoyer une autre façon de faire. Alors, la mais lui, il a trouvé ça. Il a écrit ça avec un petit et puis, il a compris tout de suite. Ah, il faut une équation de diffusion avec un petit trait que je 2099, 2099. Là, il y a plein d'autres sortes de choses. Beaucoup plus avec tout ça. Notamment les paroles. Macroscopique. C'est pas plus que moi. Non, non, c'est pas déjà, non, c'est pas.
Not formally. They go off for a year and then
Je crois que... Ah, tu bah, je pense que c'est bon, non? Tu crois pas?
a very, very good job. Oh, wow, that's good. And to the, no, not in that, but. Ways to be, or this kind of reasonable thing. As long as there is. Yes.
Bien, buenos días. Good morning. So we continue here with the second lecture of Professor Frederick. So
Thanks, Gabrielle. Thank you. I feel like I'm taking an exam with the an oral exam. That's cool. Okay. So good morning, everyone. So the second lecture that I will be telling you about has to do with yet another way of falling out of equilibrium. I want to talk about systems that if life were good with them, they would actually, if you would wait long enough, they would reach equilibrium, but for some reason they just don't get there. They never get there, or they get there in over absurdly long times that are not compatible with our observation timescales, human observation timescales. So this is a very fuzzy definition of what a glass is, but this is what I will be telling you about, systems that are just fluids, like the first system that one studies in statistical mechanics is the ideal gas. The second one, you maybe put a few interactions between the particles, dilute, not dilute, and then you try and determine the partition function. That's what you do in equilibrium. And there are many methods to do that, etc., etc. So what I'd like to do this morning, I'd like to begin by telling you about the statics of equilibrium fluids, what we know in the statics. And then I will tell you about dynamics, because if I would believe the Boltzmann distribution, glasses would never exist, because the Boltzmann distribution is based on the assumption that there is ergodicity, and precisely these systems are those that are breaking ergodicity by not visiting the whole phase space and by never being able to sample the whole phase space. So the first few things I'd like to tell you about have to do with the structure of fluids in equilibrium. And by a fluid, I mean just a large number of atoms or molecules that interact via a pairwise potential. So, yep, let me write that. Equilibrium, statics. And then I'll show you a few pictures. So I need, oops, sorry, n atoms with positions Ri, and that interact via a potential, a pairwise potential. That's the sort of model I have in mind. But before I tell you about the math and the statistical physics itself, I want to show you a few things about the structure of glasses, of liquids, sorry. So perhaps you know that if you're looking at an ideal gas, particles don't see each other. So it's completely uniform. There are no correlations between particles because they don't see each other. And therefore, given that there is a particle here, the probability that I find another one right there is going to be completely uniform, right? So it's simple physics. Of course, if now you imagine that there are some interactions between the particles, and by interactions, I mean sort of Lagrange-Jones, that is typically short-range repulsion, maybe medium-range attraction, not even necessary, and nothing when they are very far away. So short-range with a given range for the potential. Then, of course, you cannot overlap two particles. So if I'm asking, given that there is a particle here, what is the probability that I find one just next? It's going to be 0 because I don't want the two particles to overlap. So if you have a careful look at the picture in the right-hand side, this is taken from a very, very nice StatMex book, Introduction to Modern Statistical Mechanics. Then you'll see that the one particle that you have tagged in the middle gets surrounded by some sort of a layer of particles that arranges in a spherical manner around the tagged particles that you have decided. That's because you cannot overlap two particles, so they will, go around the particle. And what's happened is, if you're asking about what's happening a bit further away, well, again, your particle in the center here, you can only put particles a diameter away here, because you can never put a particle that overlaps here, for instance. That's prohibited. And you see that the more you add particles, the more they will somehow arrange themselves into spherical layers around the particle that you're considering. Of course, if the system is super dilute, this structure fades away super fast. But if the system is super dense, well, there will be some survival of this structure. And there's a way to measure this, and I just told you about that. It's the probability that, given you have a particle right here at the origin, what is the probability that you find one a distance r away? So the mathematical translation of this picture here is this curve here. And what you can see is that, of course, there is absolutely zero probability to overlap with the particle in the center. But of course, there's a peak of probability if you're just sitting in the spherical layer a diameter away. And again, it drops almost to zero, because it's not perfect order. And then there's, again, an increase of probability for the second layer, et cetera, et cetera. So this layered structure, spherical layered structure, reflects in these oscillations with these peaks that are less and less pronounced as you get away, because, in a liquid, there is no long range order. Of course, if you would be considering a solid, you would push the density very hard, what you would get would probably be just a sequence of equally high peaks. That would be for a solid. Okay, but that means that there is some order in a liquid. It's just, a short range order, and it's measured by this G of R. So very often, and one of the things that will come back a number of times in what follows, is not the G of R, this probability, but the Fourier transform of the probability. Of course, it reflects exactly the same oscillating properties. So let me flash it for you, but that's exactly the same. So that's the structure factor that's the Fourier transform of this probability density. And because I'm in Fourier space here, the first peak appears at 2 pi over sigma. Sigma, again, think of it as being the diameter of the particles or the range of the interactions, et cetera, et cetera. And of course, that's the statistical mechanics of equilibrium liquids. So I want to stress that probably this is the first sub-area of statistical mechanics that was studied so extensively, also using numerical simulations, because probably it's hard to find exactly solvable models for fluids. So this is the subfield that probably led to the biggest development in terms of numerical simulations, the physics of equilibrium fluids. For instance, I dare you to find a very good approximation, an analytical approximation that actually reproduces these curves. This is super hard. And unlike other systems in statistical mechanics, for instance, you've heard about the Ising model, you've heard about other models that you can exactly solve for fluids. It's super hard. There is no exactly solvable model available that you can use as a handle to at least to control what you're doing. Well, this is not exactly true, actually, and this is what I'd like to begin by telling you about. In the mid-'80s, when it was already, when simulations had already taken over the field of equilibrium fluids, there is a bunch of people, Frisch, Perkus, and others, that thought of a way of one exactly solvable limit for equilibrium fluids. And it's a bit of a strange limit, but as always, I told you that in the first yesterday. Sometimes you have to give up a bit of realism so that you can make analytical progress, and this is exactly what they did. So they were considering a fluid of interacting particles, so n atoms. Think of it as being a repulsive potential. And they found out, I think it's 85, Frisch, and then Perkus and others. Sorry. They found out that if you work in a space of dimension D, with D super large, you can actually do statistical mechanics and come up with exact results in equilibrium. So that's super interesting. Of course, it came a bit too late because already at that time, mid 80s and 85, everyone knew about the structure of fluids, simulations where you would just have to run the simulation to get the structure factor or the G of R. So I don't think it made much noise at that time until I would say the 90s, early 90s, where because they were mentioning that, oh, it's a nice procedure to get exact results for equilibrium fluids that are classical, but you can also think of quantum fluids, and there's, I think they have one paper on quantum fluids. And then it was taken over in 91 by people from condensed matter that thought, oh, that's a good trick. Maybe we can actually make progress for quantum systems. And that's the beginning of something called DMFT, dynamical mean field theory, for quantum systems. I would say that the next step, when it was revived and people thought it was maybe something interesting, was 99. Because there's a group in Rome that is specialized in analyzing the metastable properties of equilibrium systems in terms of replicated fluids. And by replicated, means that you couple several systems and systems together, and you send the number of systems to 0 or to 1. It's a strange limit. And of course, you cannot do that on the computer. It only works on paper. So if you want to do that explicitly, the only way that you can do that is find some exactly solvable model, work it out for your n copies of your system, your n replicas of your system, and at the end of the calculation, if everything is exactly solvable, then you're happy. You can send the number of systems to 0, to 1, to whatever. So that's when I think it was revived, and then later it was really pushed by these people. So the story I want to tell you is the story of this infinite dimensional limit that allows us to not only make statements about the statics, but also make statements about the dynamics. Because I told you, we know the statics is wrong. Okay, so let me begin by the statics and telling you why it's actually clever to embed the system of interest, our n particles, in a space with a large number of dimensions. So think of one particle here. That's, diameter sigma, that's one particle. I have to deal with interactions because I am not interested in dilute systems. I'm interested in dense systems. I want to be able to describe systems that are strongly interacting with each other because that's what's happening in a liquid. And then I'll think of the dynamics, but let's go through the statics first. Then if you think of them as hard spheres or short-range repulsive particles, then in order to have an interaction, you need another particle right next to it that is stuck to it, right? Okay, but dealing with pair interactions is easy. That's what we do in the virial expansion in the dilute limit. So this we know how to do. If we only had two particles, that would be cool. But life is more complicated, and maybe some of you have heard about Meyer diagrams, how particles interact with each other in complicated way. Think now that I'm adding a third particle into my system. So of course, I can either put it here, or I can put it there. And this is not at all the same, because in the red situation, I can view the network of interactions in my system as two pairs of interactions between two pairs of particles that are separate, because the red and the upper red doesn't talk to the lower blue. However, if I'm dealing with the black particle that is actually interacting both with number 1 and number 2, then it's complicated because I have like a triangle of interactions, a loop, and that is making my life miserable because it means that when I'm going to add particles, I will also have more and more complex structures, and that I don't really know how to handle. So the thing is, if you measure the relative volume in phase space of what's happening to the red particle, so think of the volume of the particle, so let me call that 3 and 4. So look at the relative volume V1, 4, V1, 2 divided by the volume occupied by the 3 particles together. Then you would find out that if you're working in arbitrary space dimension, this volume is actually going to be very, very small. And that's actually the reverse. It's going to be super large. So let me put -1. Yep. So if you do the calculation, and it's just geometry, this is what you find in arbitrary dimension. Okay, good. That means that if you're sending the space dimension to infinity, the probability of observing configurations in which the black particle is actually interacting with the 2 blue particles are exponentially rare in the space dimension. And you can sort of forget about them. So that's cool, because it means we can focus on pair interactions, or we can have a view of our system just based on pair interactions. So if you do that, then you can, if you have this picture in mind, you can go very far. You can actually compute the partition function. You can compute the pressure as a function of density, etc., etc. So I want to tell you a bit more about this infinite dimensional limit, but I want to show you that it's something physical. So again, I'm interested in describing a system with very strong interactions. So if I am 1 particles, I want to be interacting with d neighbors. So I don't want to be sitting in a low density limit in which I wouldn't have any interactions. So what I want to be doing is I want to be, if rho 0 is the mean density, what I want to be doing is I want to be working in a limit in which the mean density times the volume occupied times the volume of the sphere of radius sigma is going to be of order d. So, and this volume of the sphere of radius sigma is just the usual volume of a sphere, right? Maybe I'm wrong. Maybe I'm screwing. Yeah. So that density times the volume of the sphere of radius sigma counts typically the number of neighbors 1 particle has. And I want to work in a regime in which this number of neighbors is order d. Because this is what you would have in real life, that you would have, if you're a particle in the plane, you would typically have 3 or 4 neighbors, etc. Or think of an Ising model in which each spin has 2D neighbors in dimension d in a hypercubic lattice of dimension d. So this is the limit in which I want to be working. I want to be working with d going to infinity while keeping this guy here of order 1. So the correct limit that I want to be working with is exactly this one. I want d going to infinity, but phi hat fixed. That's the density regime in which I want to be working. Okay. Then in that regime, it turns out that you can implement everything that you know from equilibrium statistical mechanics, and in particular, you can do the virial expansion. Maybe, does it ring a bell to anyone? What the virial expansion is? Yeah. Not the first row, not the good students, the other ones. So the virial expansion is a procedure that tells you how to get the equation of state for say the pressure as in increasing powers of the density. So if P is the pressure, beta is 1 over the temperature, this is the equation of state for an ideal gas. Of course, if you're dealing with strongly with interacting particles, and if the density is a bit bigger, then you will have corrections that are proportional to the density squared. And if you go to higher even densities, then there will be contributions of density cubed, etc., etc. So let me write up the next term here in dimension D, though usually this is written in dimension 3 if you open a text. Oh, and there is the G of R that comes into play, because in order to find out how the pressure is affected, so think of it as being the wall of my container. There's a particle that's going to hit and create some pressure, transfer some momentum. But of course, if it is held back or pushed by some other particle, then it will modify the pressure. And the probability that I find another particle a distance r away is given by this G of R that I described before. So that would be the first correction in the virial expansion. And in principle, I have terms rho cubed, blah, blah, and rho 4, etc. And it's been almost a mathematical challenge to find the series. And there are people like McCoy that have been working on finding, these coefficients to super high order. But luckily, in infinite dimension, you don't need to care about any of that. In infinite dimension, the only thing that survives the virial expansion is this. So actually, the equation of state for an equilibrium fluid in infinite dimension is super trivial. It doesn't tell you much. It's just, you've got a pressure that is given by this thing, and there is nothing really mysterious about that. So that's the status of the statics. Of course, the G of R is given to the lowest order by the so-called Meyer function. And it only involves pair interactions. As I advertised by telling you that, yeah, but in infinite dimensions, you never have these loops of interactions because they are very, very little likely to occur in infinite. They're exponentially rare in the dimension. Okay, good. So I'm happy with that. I told you about the virial expansion a little bit. I told you about how we can neglect these loops of interactions. So now I need to do a bit better. And because there is nothing in the statics, and because glasses are an intrinsically dynamical procedure, I need at least to endow my particles with some dynamical evolution rules. Okay, so that's what I will do now. And let's go for it. So now, yes, sorry, go ahead. Oh, okay. So if you're working in 2 dimensions, you see what that means, right? Yeah, you have your particles that are on the plane. If they are in 3 dimensions, you also see what that means. They are, in a real volume. So now we as theorists have more freedom than a true experimentalist. I can think that my system is defined in 4 dimensions or in 10 dimensions. And if this helps my derivation, I may be happy. Of course, I agree with you, this is completely non-physical. But as always, it's only the end result that tells you whether this is actually a good idea or not. Whether you've thrown too much of the water and the baby in your bath, or if you've kept enough physics by doing this huge approximation of working in infinite dimensions. Right now, there's no reason for you to believe that it's relevant. I could, there is a powerful argument, a sociological argument. Someone got the Nobel Prize for this limit. So maybe it's worth it. So let's go for it. And then we'll see. This is not a good argument. I don't feel comfortable with the argument, but just bear with me and then we'll see what it predicts. And if it predicts things that are resembling physical reality, that's good. Yeah. So I'm embedding my system in a large dimensional space. So now I have many choices for the dynamics. The only thing that I want is to endow my particles with dynamical evolution rules that respect the detailed balance with respect to the Boltzmann distribution. So I want to make sure that if I wait long enough, this is going to be the probability distribution. If everything would go right, at least, I would like this to be the stationary distribution, equilibrium distribution. So fortunately, Laetitia yesterday mentioned to you one these Langevin equations that do respect detailed balance, that are consistent with the sampling of the Boltzmann distribution. And let me write one of them. So there was some friction. Maybe I will write them. Some friction, some forces created by the neighbors, and there is some noise here. So I don't think it really matters if we're working in the overdamped limit or underdamped limit, meaning whether I keep this inertial term or not. I don't think it would really matter for the physics. In terms of physics, if I'm removing that term, it means that the system that I'm describing is made of big micron-sized colloidal particles evolving in a solution, for which the Reynolds number is so low that you can actually neglect that piece. So that's what I'll be doing, because it's making my life simpler, and hopefully at large times, none of the actual physics that I'm going to describe depends on these short time details given by the inertial time scale, right? The other thing that I will do is I will set the mobility or the friction coefficient gamma to unity, because it's simpler, but it's there, of course, right? So my time is measured in units of gamma. So this is called overdamped dynamics, overdamped Langevin dynamics, and life is actually very simple with that. So now, in principle, as I told you, because there is detailed balance, because the noise here, the injection of energy into the system, is intimately coupled to the dissipation channel. So whatever is dissipated is returned to the bath, and whatever the bath is giving to the particle is eventually dissipated back into the bath. So this fine balance between injection and dissipation is detailed balance, right? It's equilibrium. So if there were no problem of ergodicity breaking, I would be sure that I would be sampling at the very at late times, after the relaxation time has elapsed, this Boltzmann distribution. So now at this stage, I need to make a small interlude that connects with what Laetitia was telling us about yesterday. So let me tell you about a work by Mazur and Oppenheim and Van Kampen and Oppenheim of the 70s and 80s. And it's exactly what Laetitia was telling you about yesterday. So think of the following system. You've got one big micron-sized particle here, and lots of water molecules, small water molecules. Think of this guy having a big mass and these ones having small masses. Then you see that your big particle will be slow. It will be sluggish. It will have super slow dynamics. And anything that Laetitia has been telling you about the effective dynamics of this big particle here in the middle will hold. That is, it's going to be slow, and because it is so slow, I can think of the bath as being instantaneously in equilibrium with the blue particle at a given location, not evolving dynamically. So the physics of this is going to be rather simple. And if I would try and eliminate the bath degrees of freedom, I would end up on the Langevin equation for the big, heavy particle. So why am I telling you that? Well, it's because I'd like to do something similar with my dynamics here for my particles. So that's the dynamical evolution for one particle. And I have to somehow think of a way to describe the dynamics, say, of 1 degree of freedom, so that I can get some sort of effective description of, say, one particle or 1 degree of freedom, forgetting about the rest, because I know I cannot solve n-body dynamics. This is too hard, right? So maybe if I eliminate n-1 particles or some degrees of freedom, I'll be able to describe the effective dynamics of 1 relevant degree of freedom. So now things are complicated, right? Because I am working with n particles, and I have this added technical difficulty that I'm working in a number of space dimensions that is super large. So one natural thing to do would be to think, okay, I will tag one of the particles and I will consider the rest of the particles as being a bath, and I will try to write some effective dynamics for that particle. But then you see it's not quite right, because this looks to be a summation over n-1 particles. Well, it is a summation over n-1 particles, but that isn't true, right? We know it isn't true. Effectively, only d terms contribute that summation, because I know that my particles typically are interacting with d neighbors. So in that contribution here, I don't have n particles, I just have d. So it's okay, I can eliminate the other particles, but then it's a problem because my vector, my position vector, also has d components. So I cannot, trace out as many degrees of freedom as the number that I keep. It doesn't mean anything. So what I will do is I will tag 1 degree of freedom, say the x position of one particle, and I will consider, it's a brilliant idea, not mine. Say you tag one of the components of the position. This is the interesting degree of freedom. And what I will be considering as the bath are all the other components of the given particle that you're considering and of all the other particles. And that I will call the bath. Yeah. So that's pretty simple here. What I have to do, at least, then we'll see if we can implement that easily. But I am tagging, say, the x position of one particle, and I will try to integrate out the rest of the bath, the harmonic oscillators of Laetitia yesterday, to get an effective Langevin equation for my tagged degree of freedom, say the x position of particle I. Okay. So this is not so hard to do, because we know how things go. We know that, because Laetitia wrote it yesterday, actually, we can anticipate the form of the equation for that particle. We know that generically there will be some memory kernel. And why do I know that? Well, it's because if the particle is immobile, it shouldn't feel any force, right? And it's only going to feel some force if it is moving in the path of the other particle. So I'm expecting that there will be some memory kernel of that form, and there will be some extra noise here. And it shouldn't be anything else. Of course, now you have to go back to the literature of the 70s to find out what is the expression of this memory kernel. Well, the memory kernel is given by some sort of Green-Kubo relation that is expressed in terms of force-force correlations of the bath. So I only need to look at the force-force correlations of the bath, and that will give me my memory kernel. So it's a bit of a leap here, but it's really literature from the 70s and 80s, nothing really fancy. So this will be, for instance, the force exerted on particle I along direction alpha times the same. And that's the force created. Fi is the force created by the rest of the degrees of freedom, those that I'm not tagging, those that I'm not fixing for the description of my dynamics. So, of course, I'm expecting, at least in a regime in which I'm not breaking ergodicity, I'm expecting that the dynamics is going to be consistent with detail bounds. So I don't have any freedom for the noise. The noise must be consistent with this detail balance. So, okay, I know that the noise correlations at time t and at time t prime should also be given, maybe up to this, by the same memory kernel that governs the dissipation, because dissipation and injection are completely entangled in equilibrium. All right, problem, I don't know M. Yeah, it's a problem because it's okay, it's probably true, but it's still very abstract. I don't know much about the dynamics here. So we can do a little better. Now, because M involves forces, and forces involve at least two particles, I need to think a little bit more. And maybe instead of tagging 1 degree of freedom, I will tag 2 degrees of freedom and look at their coupled dynamics. So I will say, take now look at, say, these 2 degrees of freedom, fixing I and J and alpha, and I will write some sort of a similar equation for these 2 degrees of freedom and see how they talk to each other. Of course, it's almost the same equation. There is nothing that should be really different here. If I'm going to write the equation for this guy, then of course it should have this memory term here. But because now I'm fixing also what's happening to particle J, I should think that it also has it also has the component alpha of the force between I and J plus noise. And I have something similar for this. Except I have a plus here, plus noise. Still didn't make much progress. I just, went from the description of 1 degree of freedom to 2 degrees of freedom. Yeah, but it's a big step actually, because now once I have the description of 2 degrees of freedom, I also have the description for the relative degree of freedom. And that's interesting for me because this is the right way to get some information on the force statistics. All right. So I have one equation that tells me about the diffusion of a particle in a bath made of degrees of freedom of the other particles plus its own other components. And I also have a similar equation for the relative distance between 2 particles along a given axis. So once I have this, well, in principle, you see what I have to do, right? M is unknown. It is unknown. So what I should be able to do is solve this dynamics with fixed M, right? Determine the force-force correlations, because if I have the relative dynamics, I can get the force-force correlations and get, therefore, a self-consistent equation for M. So I can solve the dynamics at fixed M, determine force correlations as a functional of M, and use that M equals this functional of M. That's exactly what you would do in mean field, right? You assume that you know the magnetization, then you work with it as if you knew it, but you don't, and then you find a self-consistent equation for that magnetization. Here it is exactly the same, except that it's a bit more complicated, because instead of having to find one number, I have to find a full function. So it's mean field, but for a function, because I'm looking at dynamics. But I hope you see the structure of the theory here. First, you you work with arbitrary M that you don't know. And suppose that you're very good that you can solve the dynamics for arbitrary M. Then once you solve the dynamics, you can also determine force-force correlations. Good. And these force-force correlations are exactly given by M. So that gives you the self-consistent relation for M, and you can solve for M, and you're happy. Yeah. And then at least you've answered what is the effective dynamics of one particle of 1 degree of freedom in a bath of other particles. So why am I happy if I get M that way? Because if M is known, then from this equation, then you can find the diffusion constant of one particle, because it's going to be given by M or something like that, right? Or the integral of M. So if this is true, so I'm not going into too much into the details here, but I don't remember if you did it yesterday, but once you have an equation of that form, you can Fourier transform because it's a linear equation for Ri. So you can get Ri as a linear expression in the noise. And you can take the square, average, and you get the diffusion constant. So let me give you the expression of the diffusion constant for particle I along the alpha direction. It looks like something like that. And I'm restoring the gamma just because it's nicer. Sorry, that's one. And here I have the integral between 0 and plus infinity of this guy. Okay. So if I'm able to solve for M, then I get the exact expression of the diffusion constant for one tag particle. So it's impossible, actually, to solve for M as a function of time. This is too hard. That's at least people that are very strong have tried, and I don't think they have succeeded. But it's not a big issue, because maybe you don't need that much information. Maybe you only need, say, the integral of M at infinite times. And that, on the other hand, is something that you can get with relatively low technical cost. So I'm not showing you how the calculation goes, but there is a technique that allows you to get this integral here. And what happens is twofold. If you're high density or T low, it turns out that this guy here is actually infinity, which means that unlike what Laetitia was telling you yesterday, this memory kernel doesn't relax to 0, not even as a power law. It's just, it doesn't relax. And what's happening is that the diffusion constant just vanishes because somehow the dynamics gets frozen. And that's for phi larger than some threshold. Phi, let's call that phi dynamical. And you can find at least for hard spheres and some other simple potentials, you can find an expression for this threshold density at which the diffusion constant just stops, it becomes 0, just vanishes. However, if phi is lower than this dynamical threshold, then this integral here is finite. D is non-zero, and the particle diffuse. Of course, they diffuse more or less depending on density, but the dynamics is ergodic. So this is actually a very nice example in which you can, okay, you're working in infinite dimension. I know this is strange, but what you see is that if you would do the math to the end, you would see that in infinite dimensions, if the density, the rescale density, exceeds a given threshold, it kills the diffusion constant and the dynamic freezes completely. So if the dynamics freezes, it means that in this regime, none of what you know from equilibrium stat-mechs applies, because you just violate the basic hypothesis, basic postulate of Boltzmann, which is ergodicity. So that's a very good thing, because it seems to be indicating that, at least in this strange infinite dimensional limit, that you've got a regime in which you break ergodicity, and that's very reminiscent of what you observe in a glass former. So now you can ask all sorts of questions. Yeah, but what does it mean? Working in infinite dimensions, that is spurious. Actually, is there any experimental sign of the existence of a given density that acts as a threshold, as if it were a phase transition? All these things are legitimate questions. But already this is very satisfactory that there is one calculation that shows you that there are two regimes, even it's a bit of a caricature, this calculation. So let me comment a little bit more on this result. So this result was found by this route, I think maybe 15 years ago, 10 years ago. It was first found by a purely static route. So here I'm using dynamics because I feel more comfortable with dynamics, but other people found this result, the existence of this ergodicity breaking transition, just by looking at the metastables, by investigating the structure of the metastable states in the equilibrium distribution. So actually, there is enough information in the equilibrium Boltzmann distribution that tells you that indeed the diffusion constant, which is a dynamical quantity, should vanish above as a given threshold. So maybe this is consistent with static replica calculations. So the method was found by Monasso in 95 and used by Parisi and Mézard in 99. So now we're left with something that is a bit of a, working in infinite dimensions, a bit like mean field. So we know mean field sometimes has spurious predictions. So if you're a normal theoretician, then you want to confirm this result by other means. Maybe you could put your system on a computer, but you don't want to put an infinite dimensional system on a computer, though some people have done that. For instance, or say dimension 5, 6, 7, 8, etc. Or you can think of other methods that would tell you about the finite dimensional dynamics and see if you get consistent results. So you should never be content with just one method, because this one certainly has maybe flaws. And the picture that is behind this vanishing of the diffusion constant is actually very, almost too simple. It tells you that if you're one of these particles that you tag, one of these degrees of freedom, your dynamics gets stuck, and the underlying mechanism is that somehow the rest of the environment is building up a harmonic trap within which you're fluctuating. And a harmonic trap has infinite walls, right? So you can never escape a harmonic trap. So that's consistent also with the idea that dynamics is completely frozen, which is not something that is absolutely observed neither in simulations nor in experimental reality. So you have to take all this with a grain of salt. Probably most of the physics is there, but there are still some things that you would maybe like to, look a bit more carefully at. In particular, yeah. So I'd like, at this stage, I'd like to say, okay, we accept that there is this infinite dimensional result, but let's see if we can find alternative routes that would somehow give an alternative view or complementary view of the same question, but preferably in finite dimensions. Don't be fooled. I will do that in 3 dimensions because that's, the assignment, but I will have to do approximations. So at some point, these are difficult problems. You have to do approximations. And whenever you do an approximation, you're never sure that the end result is whether the end result is a byproduct of your approximation or whether it's a true physical feature. So let me just tell you a bit more now about alternative routes. I will probably not be very detailed here, but let's go into these things. So I write this is an alternative, but it's historically wrong. It's actually the first thing that was done. So exactly the same words as Laetitia yesterday. So projection techniques. So the idea is, okay, I have the same problem, same dynamics, same question, but let's stick to physical dimensions. You know, I'm still working with my nice little particles, colloidal particles in a fluid in which I have thermal noise, and my goal is to understand what's happening, say, to what is the fate of ergodicity in the system. So instead of looking at the diffusion constant, I will look at some other quantity because that's historically what was done, and also a little easier given the method I'll be using. I'll use not the static structure factor. So I told you already that this S of k is the Fourier transform of G of R. G of R is the probability that given you've got a particle here, that you find one a distance r apart. And that's also given by the density fluctuations in your system, where delta rho of x is just rho of x minus rho 0. So delta rho of k is just rho of k minus what's happening in the 0 mode. Yeah. So the structure factor that I plotted for you a bit earlier, that looks like this also, is what tells me about the statics. And it's density correlations in equilibrium. Of course, you can immediately think of a dynamical analog for that. And the dynamical analog for that would be S of k and t, exactly the same density fluctuations, but at unequal times. And if these density correlations decorrelate, if they tend to 0, I'm happy, the system relaxes, and I have an ergodic system. If, on the contrary, these dynamical correlations get stuck and reach some plateau value, even if I'm sending time to infinity, then I'm breaking ergodicity. Okay, so what I expect for this S of k is typically this as a function of time. It should decay to 0. Of course, if I'm increasing the density, maybe it will take a bit longer. And the question is, if I keep increasing the density, what's happening? Is it going to saturate? Is it going to develop some interesting structure? I don't know. And the goal is to actually determine this curve, the structure factor as a function of time. Again, I will not be able to do that exactly, but I will just sketch a few steps that allow us. Maybe there's 1 over n. Sorry, I'm using wrong normalizations. Okay, good. So let me show you a little bit how these things go. It's not particularly easy, but I will try to give you the elementary steps. So first thing, because I'm going to be working in terms of the density modes, instead of looking at individual particles, maybe it's more clever to look at density modes from the start. So if you've got, if I am defining the local density, local fluctuating density by a sum of delta peaks, it's called the empirical density. Then what I see is that what I can derive is that it's obvious, as I said yesterday, that there will be some local conservation equation for the density. Cannot be otherwise. And you can actually show, by using a bit of stochastic calculus, that the local particle current has, because the colloidal particles are diffusing, there has to be some thick contribution. You know? There is a diffusion process, so I need to be verifying fixed law. There is also the drive governed by the other particles, produced by the other particles. So that's the density of particles times the force density. And the force density is at location X is given by the integral by the force around X created by the other particles. And of course, there's some noise, and you can work out the noise exactly. So this equation is actually exact. It was written as such by David Dean in '96. Earlier versions that are similar but not quite were written by Kawasaki a bit before. But that one written by Dean is really about the empirical density. So it's really some exact equation. So it doesn't tell us anything else than it's like a summary of the individual equations in which you would forget about the particle labels. There's nothing more. Forget about the information about particle labels and you end up on an equation for the density. Same physics in there, just you don't need that information on the labels, so you end up on this equation for the density. Of course, you see from here that the thing that matters, if I am going to be, then I can Fourier transform this thing. Maybe that's kt, sorry. And this is going to be given by ik times the local current. So I'm not writing the Fourier transform explicitly, but the thing that I see immediately is that if I am going to look at the structure factor, that is, I'm going to multiply this with the density fluctuation at time zero, an average, then the noise contribution in J will not matter because the noise is evaluated at a later time. So let me just write the equation for this. And I have the local current times this. But because delta rho at time zero is not correlated to this, that contribution will not appear in the average. And the only thing that will matter is that part of the local current. Let me call that J deterministic. Maybe not a very appropriate, but at least that tells us exactly what we have to compute. So my task now, if I want to obtain an equation for the structure factor, is to determine this guy. Okay, so I want to determine this, and it's hard, and I will not be able to do that unless I make some approximations. So before I do approximations, I want to show you one tool that people have been using since the 60s, which are the projection tools, projection operator tools. So what should I do now? Maybe, yeah. So the main idea for the projection, if you're doing some geometry or algebra and geometry, you know what a projector is. You have got a vector, any other vector has a component along the vector that you decide, and that defines a projection operator. So here you have to think of all your physical observables as making up a big vector space. And what you're interested in that huge vector space of all possible observables, or what's happening along density. Because this is density that you're interested in. It turns out that density is a conserved, so it's a slow mode. So maybe if you integrate out the rest of the degrees of freedom and work only in the projected by projecting along the density, then you eliminate the fast degrees of freedom. You have the hope of eliminating the fast degrees of freedom, and you just focus on the slow degrees of freedom, because if density is slow, then you will be focusing on that. Of course, the problem is that if density is slow, density squared also is slow, but density squared is not density. So by projecting onto density, I will forget about some of the slow variables as well. I don't really have any other slow modes here because I don't have conservation of momentum, so I don't have like a stress tensor to take care of. The only slow thing, physically slow thing, is the density. What does it mean that it's slow? It means that the relaxation rate of the density increases with the system size, with some power of the system size, which you can see from here. If k goes to 0, this is almost 0. Yeah, okay, but you see, I am abusing you somehow because I'm telling you that there's a slow mode, blah blah. But think of it: what is the slow mode in glass formers? It's not really the one that concerns the whole system. It's what's happening locally, in which one particle gets somehow trapped by the others. So yes, I'm after slow modes, but I'm after slow modes that are at the very small scale, not super large scale. But still, I will assume that density is a good variable to project any other observable on, and I will define a projector. So if A is a physical observable, I define the projection of A along the density as being the scalar product, and the scalar product here is just the equilibrium average of A along the density times the density, and I divide by the scalar product of the density with itself. So that defines a projection operator in a big space of observables. It's not an approximation, it's just a definition, okay? So what I'll be trying to do now is I will try and use these projection operators to determine. You had a question? No? You have the right to interrupt me, otherwise it's hard to speak for an hour and a half without being, interrupted. Just yeah, you should. So what I'll do now is I will use this. Yes, thank you, Jose. Yeah.
Could you write down the questions for the group?
Yeah.
Yes. Okay. Last term is the first one is that.
Yeah, that's diffusion.
But this is not a consequence of the viscous term and the random force.
Yes.
When we know the random force accounted for.
Exactly. But it's not accounted twice. It's accounted once in two separate channels. Yeah. So when you go from the individual description to the collective modes, in which you forget about these. Okay. Think of particles, right? Put them in a very inhomogeneous state, and let them diffuse. You will agree probably that the density profile would smoothen and flatten. Yeah. So that is not described by the noise, it's described by the deterministic term, fixed term here. Yeah. So, but you need that, right? If they wouldn't move, and that's driven by the individual noises of the particles, that pushes them away. But at the same time, you've got I mean, these are fluctuating quantities, so you still have to remember that they are fluctuating quantities, and there has to be a remnant of that randomness, and that's this exponent here. Maybe I can prove this equation if you like. You want me to prove this equation or no? Okay, okay. Yeah, it would break the flow, and thanks. Good. So this is a projection operator, and the thing that I don't really know what to do with is this right-hand side here. Because I don't know, this is a high order correlation that is hard to make sense of. So what I will do is I will try to think of this deterministic current as an observable, and I will split the deterministic part of the current into one part that is along the density mode and one part that is perpendicular. So I would project this deterministic part of the current along delta rho and look at, and then split from the rest. So in particular, so if I'm going to do that, what will happen is that well, by definition, right, this is just this, And for the moment, it's nothing really. I'm not doing anything. I'm just working my way through the various observables. So I want to be able to separate in that deterministic current the part that is really along delta rho and the part that is perpendicular to delta rho. Because if I can do that, you see that I will somehow be able to close, or it looks like I'm closing the equations. Okay, so fortunately, this scalar product is just an equilibrium average, so I can compute it. It's really not hard. I'm giving you the answer, but it's really not hard. All right, it's just an equilibrium average with respect to the Boltzmann weight, so you can work it out on your own, not hard. So that means that this guy here is going to be given by this part, oops, sorry, delta rho divided by S. Of course, there's the rest of the current, and I have to take care of that. I cannot just eliminate it. But what I will do now is I will split the current into two parts. This J depth which occurs, I would write it like that. And I'll see what I can do with the rest here. That is, these are all the annoying degrees of freedom that I really would like to eliminate. They are not the ones that are along delta rho. They are along some other vectors. Okay, so if you do that, then you have to work a little bit. It's not completely trivial. You have to look how things evolve in time, etc., etc. And there are some identities. In particular, any observable A evolves according to some linear evolution plus noise, where this W dagger is the adjoint of the Fokker-Planck operator. So this is where it becomes a little messy, because you've got to use some identities between operators. You've got to be using, things that are not very elegant. But let me just cut to the chase and write what the final equation, when we do that, looks for the density correlations. So if I'm using the splitting of the current, I can write some equation that looks close, but that isn't, for the structure factor. It looks like this. Yep. Plus some memory term. Again, not surprisingly, S of k t divided by S of k, t prime, sorry. And the problem now is that by eliminating all these perpendicular degrees of freedom, perpendicular to delta rho, I have a very, very messy expression for this memory kernel. Let me write it for you. And here F is even more ugly than you would think. It's given by a combination of these projection operators and delta rho. Okay. Okay, good. So, or if you like, delta rho plus t k squared over s of k. So a bit messy, but there is a bit of joy, because you've got an exact equation for the evolution of your structure factor. It's exact, but again, it's not solvable because you have no clue what this m is. So so first, I have to be honest with you here. This proof, well, not exactly in those terms, but can be found in the paper by Grzegorz Samel and Hartmut Löwen of '91, and it follows earlier papers in which similar proofs were done with Newtonian dynamics. But here I think it's it's nicer to think in terms of colloids. Though there are additional, unexpected additional technical complications that have to do with the this memory kernel that you have to be more careful with than in the usual Newtonian dynamics case. But let's leave that aside. This is the end result. I have a very, very horrible memory kernel here that I have to determine if I want to solve for the dynamics. And this is where you have to do, you have to be pragmatic, and you have to drop your requirement to do exact stuff. You have to, let loose a little bit. So many things that people do, for instance, is that, okay, maybe here in the exponential, the 1 minus p, let's take it a 1. Let's forget about the p. So that then you go back to an evolution in terms of the original dynamics easier. Then you're still stuck. You have to do more approximations because, as you can see, this M involves a host of density correlations. So it's going to be something of order 4, and then you've got to do some closure, blah blah. There is a bit of cuisine here, and I'm not going to go into that because I'd like to write the final equation that people arrive at by looking at the various possible approximations. So before I do that, I would like to tell you about 2 super nice reviews on mode coupling. Yeah, this is called the mode coupling equation. And I particularly like the one by Lisbeth Janssen of 2018. And there is a more technical one by Gregor Samel in 2013. So let me, not dwell too much into the approximations that have to be made to arrive at something, and let me write the final equation that people reach once they have somehow simplified this memory kernel. So there is this deterministic evolution here for S, for the dynamical structure factor, and there is a memory contribution that involves, well, a complicated memory kernel that luckily people are able to express in terms of the dynamical structure factor itself. So I will write it in full, but I will not do anything with it. It's just because I think it's nice that you see it. Nice, just not to scare you, right? But just so that you know that it's not so easy. So this is what it looks like. C is the direct correlation function. I will tell you in a moment how it's expressed in terms of the structure factor. The nice thing with this expression is that it is expressed, the memory kernel is expressed in terms of the dynamical structure factor itself. And then there is a final term here. And C of K is basically 1 over the structure factor. C of Q is 1 over the structure factor. So that's called the mode coupling equation. And once you get there, you can feel that you're happy. You could think, oh, relief, I have finally reached an equation in which I have somehow a closed equation just for the dynamical structure factor, just have to solve it. But it's still messy math to actually extract some physics from this equation. It's a nonlinear integral differential equation. Solving it numerically is a mess. It has all sorts of strange aging properties. So really, this is a difficult equation. So because I'm not interested in whatever beauty there is in the actual dynamics, I'm only trying to find out whether anything strange happens at large times. Does my dynamical structure factor relax to 0 or not? So that's the only thing I want to do. So I will do one more approximation, and you'll see it's actually not so hard to get some answer about that. The last approximation, of course, now you see that this equation requires the knowledge of the statics. So I would need, if I wanted to solve it, I would need to know the structure factor S of K, which for a fluid, unless you're in infinite dimensions, you have no exact expression for. So one way to proceed is to think, oh yeah, but you know, I plotted for you the S of k as a function of k. And it looked like something like that, right? So what I will do is I will say, yeah, S of k is just this. And one peak around some k0, that is 2 pi over sigma. Sigma is the range of the interaction potential. And I'll plug that into my equation and see what comes out. If something reasonable comes out, I'm happy. If not, I know one has to do better, but to do better, you have to do things numerically. So I am going to assume that S of k is just 1 plus some amplitude that I don't know, times a delta around k0, and k0 is a wave vector amplitude around 2 pi over sigma. You know, the wave vector corresponding to the first shell around my tag particle that I began with. Good. So if I do that, I inject that into the equation, then it's possible to find an equation for the ratio phi k0, which is going to be given by this. Oh, I shouldn't write this. I shouldn't write this, but it's ugly, but I'm still doing that. So I shouldn't do things ugly. I should do them clean. I'm going to write an equation for this guy. And I will inject into that equation the hypothesis that I do on the form of the structure factor. If I do that, you have to believe me, this is the equation that I get. Relaxation. And there is, the memory term takes a not too complicated form. Tau, t minus tau, sorry, times d tau phi k0 tau. And lambda here is something that is a function of temperature, density, A, etc. I'm not going into the details, I'm not interested. So that equation, however, has a structure that is easier to understand. It's called the schematic mode coupling equation. And from there, you can already guess a few things. And in particular, if you assume so phi, what I expect is phi relaxes to 0. Okay. But what if it doesn't relax to 0? So I will assume that it doesn't relax to 0. I will assume that phi at infinite times doesn't relax to 0. Say it goes, say, to some threshold level, to some level f. And if it reaches some level f, then this equation that I have here allows me to find a self-consistent equation for the level f. Just by plugging the asymptotic behavior that I expect, and this is what I get. And you can almost do that by visual inspections, almost. And you can guess the origin of the various terms. This term here comes from the relaxation term here. The phi squared here gives me the f squared, and you have to be a bit more careful. The integral times this derivative gives me the 1 minus f term here. So if it reaches a non-zero level, this level is a solution of this equation. And that's an equation that is a quadratic, so it has two solutions, right? Well, three actually, but f equals 0 is a solution. Yeah, so there is a regime in which things relax to 0, so I'm happy. But there is also a possibility if lambda divided by this number is larger than 4, f gets to a non-zero limit, is non-zero. So what this is telling me, and I think this is very important, is that if the temperature is low enough, what's going to happen is that instead of relaxing to 0, my dynamical fluctuations freeze into some state. These are now two proofs or two clues that something is happening in the low temperature or high density regime. because I had this one infinite dimensional calculation that tells me high density things freeze, diffusion constant vanishes. Now I have this uncontrolled approximation, but at least it's in 3D and it's reasonable because, you know, I'm looking at density fluctuations and slow modes, etc. And it tells me that if the density is high or the temperature is low, S of k relaxes to something that is a fraction of the initial structure factor at t going to infinity, which means it doesn't relax. It doesn't relax to zero. And again, that's a proof, or that's a clue that there is some sort of aggregativity breaking taking place here. So what I have here is, I wouldn't say this is another smoking gun, but it looks like one. I have two super different approaches that somehow converge towards the same physics. So in these systems, what I have, you know, maybe it's time to summarize a little bit because we're, you know, approaching the end. What I have shown to you is that if I take a bunch of particles interacting via pairwise interactions, if I look at the dynamics in the high density or low temperature regime, what's happening is that eventually the dynamics freezes. So it's a strict freezing. So that's not good because this is not what is observed neither in simulations nor in reality, in experimental reality. But still, it's a very good sign that something strange is happening to the dynamics. And I think everyone here is ready to accept that maybe going to infinite dimensions is a bit too much. Maybe the existence of a threshold is something that is a spurious effect of mean field of going to infinite dimensions. And maybe the reality is more like a crossover. Yeah, probably. In this mode coupling approximation, in which I do a host of uncontrolled approximations, at least I'm in 3D, but I get similar physics. And you know, when clues add up, you start believing that maybe there is some truth to all that. So maybe let me just conclude by showing you a few graphs of the solution of these equations, and that would be a good way to conclude. So I took these graphs from the review of Lisbeth Janssen. They are just stolen directly, okay? But they're very nice. So this is a plot of the viscosity as a function of the reciprocal of the temperature for some fluids, and you see that I mean, glass forming is something real that happens. There are some materials for which just changing temperature by a factor of 2 leads to their viscosity or a diffusion constant to vary by, I would say, 10 orders of magnitude, 10, 12 here in particular. So it's a real phenomenon. So now the interpretation of what I have been telling you is the following. If the density is going to be low enough, if the density is going to be low enough, you can always find mechanisms by which you relax density fluctuations. And this is what is shown in the upper left plot, in which you see that, yeah, eventually particles rearrange and you can relax density fluctuations. However, if you go to too high densities or too low temperatures, what's going to happen is that you've got a sort of trapping mechanism. In the infinite dimensional approach, it was in the form of an effective harmonic potential with infinite walls. But in this mode coupling approximation, I have personally a much not as good as an understanding as an infinite dimensional case, but I can see that the physics is going to be the same. Things don't relax, and you've got some sort of local trapping of the particle. And the thing that is maybe interesting is to look at the solution of this mode coupling equation for various temperatures. Purple curve here is what's happening at high temperature in the liquid. High temperature or low enough density. Low doesn't mean that it's dilute, right? It's a liquid, so it's dense, as dense as a solid. And you see that density fluctuations, that's S of kT divided by S of k, they relax to 0. If you're slightly increasing the density, you see that the relaxation still occurs, as you would expect, but it's a bit slower. Nothing strange. It's okay. But what the mode coupling approximation predicts is that there is one density or one temperature at which your density fluctuations reach this F plateau value, and they freeze and don't relax anymore at all. So the existence of this plateau is perhaps an artifact, is likely an artifact of this approximation, because people, in particular Lisbeth Janssen, has shown that making the approximation more accurate lowers the value of the plateau, etc. But at least you've got some interesting, you know, it's almost, I would say, almost an explanation of the existence of a glass. And I would like to conclude by telling you why this probably isn't the end of the story. One important feature, if you look, because most of the interesting physics of glasses is done actually by simulations now. And what you observe in numerical simulations is that there is absolutely non-trivial structure that is occurring as you cool down a system below these threshold temperatures or above these threshold densities. What's happening is that somehow there are arrangements, local and extended arrangements of particles that talk to each other, by which collectively rearrange and that lead that completely control the relaxation of the process. And these dynamical heterogeneities, as they are called, are accounted for neither by the mode coupling theory nor by this infinite dimensional approach. So if you feel like it, go for it, because that's an interesting topic. Thanks for listening that much. And if you have questions, I'm happy to take them, of course.
Any question? Comments?
Thank you for the talk. I have the following question. I am thinking of granular media, yeah? And in that case, these closed circles of three spheres or so is the rule, not the exception. What does it change?
Okay, so I'm not an expert. Maybe your neighbor behind is better suited than me to answer. But if I would think of granular media, zero temperature limit, right? Then you can, it's a jamming phenomenon that you're observing. And actually, these infinite dimensional techniques also actually have much better results, I would say, for jamming than they have for glasses. Yeah, so there is a very, very nice review. I think it's in the review of 2010 physics report, I guess, by Zamponi and Parisi, and the jamming calculations are detailed there. Am I right? It's in the review, I think, yeah. So, but it's actually surprisingly good mean field for these jamming regime, surprisingly.
Okay, the final question. It's just a technical detail in the equation for the structure factor time dependent.
Yes.
That you need the direct correlation function. Is that the static direct correlation function, or it's the...
In this equation here?
Yes. The C is the static?
Yeah, it's the static.
Okay.
Yeah, it's the static. It's the direct correlation function. It's just the inverse of, it's just smoother to write this in terms of C than in terms of S, but I could have written it in terms of S. Yeah. Yeah, so you need, in this equation, so you need as an input the statics, because that's how you construct your projection operators.
Okay, thank you, Frederick. We continue the discussion in a coffee break.
No, cansado. Puede, no, ya son como, ¿no? Pero más o cosas. You know, that's a good question. So, usually, when you have a finance, things behave exponentially, but it's T over time with that thing, right? And that's maybe relaxation is not the main thing, but suppose the relaxation time never relax. Then it's exponential just is one. And then whatever function that should relax, stop relaxing. So for me, it's the same as saying that the relaxation time goes to infinity, that it doesn't relax to zero. So, density fluctuations, right? At time two, how they density fluctuations at time two. So if you've got infinite memory, what's happening at time zero is always correlated with time two. But in principle, things relax and move around. Yeah, yeah, yeah. So it's really, yeah, for me, it's synonymous. If it doesn't relax to zero, it means there's a problem. And if it doesn't relax, then it's not, mixing. Exactly the same. So exactly the same. Exactly the same. So I have two approaches that give me same physics. So, yeah. That's the idea.
Et m'a dit la dame,
Ouais.
j'ai depuis la dame.
Oui, oui,
Ouais, voilà. Elle m'a dit de prendre le photo.
on va regarder de mon côté, il en vend.
Oui, bien sûr. Non, non.
Bah, j'essaie de.
Oui, voilà.
Parce que qu'il y a son travail. Et après, toi, tu travailles. Ah, les trucs de protection. Et à la fin, c'est qui? Tu vois, mais
Espera, problema con el botón de...
Pero para que yo no haya iPhone. Porque yo lo conocí.
Ahí está. Okay, so thank you for coming for the second lecture. So let me start with a brief summary of what I did yesterday. So yesterday I told you about the coupling of a system to an environment and how to derive an effective equation that rules the evolution of what you call the system, what you choose to be the system, and how the effect of the bath on it appears, modifying the just Newtonian equations that you would have for an isolated system through friction and noise, and that this friction can be retarded, so there can be a memory term there, memory kernel in the integrated friction that appears, and the noise can be colored, we call it, correlated in time through a non-trivial kernel, which is the same that appears in the friction term. that is this function gamma of time difference that I introduced yesterday. So this is what we did. We derived a generalized Langevin equation, and Fred was using today as well generalized Langevin equations coming from approximations or treatments done on systems of particles in interaction. So there you could see that these kind of equations appear in, in different areas, and that certainly very useful to describe the behavior of many body systems as well. Now, the generalized Langevin equation has an acceleration term like this, mass times acceleration, retarded friction, color noise, which could be possibly multiplicative, so multiply a function of the variable itself. And then we talked about some simplifications. So dropping this inertial term and going to the overdamped limit, which is the version of the Langevin equations that most probably you're more used to seeing. And then the Markovian approximation, meaning that this kernel gamma is not depending on times in a non-trivial way, but just a delta function that tells you that correlations occur only when the times are identical. And typically we work with additive noise, but also today Fred was showing you equations for rho, where the noise was multiplicative. So there you could see, and also yesterday, that multiplicative noise equations are also very relevant to describe physical systems. So today, what I'm going to do is I'm going to talk about other ways of dealing with these situations. So situations of problems that undergo stochastic dynamics due to their coupling to an environment. And I will discuss these other ways in their most general form or through approximations. So actually, I will start through telling you about the Fokker-Planck or Kramer's equation that possibly many of you know already, but let me, for the students and also to recall certain assumptions made when deriving these equations, show you the derivation of these equations. So you will see what these equations act upon and how they look like. And basically the reason why I'm doing this here today is because this formalism is similar to a formalism that is used in the quantum problems, which is called the Lindblad equation. And what I want to stress here is that both Fokker-Planck-Kramer's equations and the Lindblad formalism for quantum systems in contact with environments make a very big assumption, which is an assumption of Markovianity. So there is no memory, no color noise in any of these two approaches, two ways of treating these problems. So they're restricted. But still, they're restricted, but they apply to describe, cases where this Markovian approximation is acceptable. And then I will, if I have time, I think I will have a little bit of time to introduce the generating functional formalism, which in the classical literature it goes under the names, an acronym that corresponds to the names of the people who discussed it. And I will mention only briefly the quantum version of this. Well, this one is approximate because it makes this Markovian approximation. The other one is not. So this is generic, and with these, both the classical or the quantum one, you can treat problems with, non-local in time friction and color noise and so on and so forth. So let me start by this Kramer's Fokker-Planck equation derivation, because the Lindblad I will only sketch it a little bit, but it's kind of similar. So differently from what we did yesterday when we were focusing on the trajectories, individual trajectories of the particle, both in position and velocity or momentum, here what we do is that we try to understand how does the probability density of a position and a momentum, so a joint probability density, depends on time. How does it evolve as a function of time? So this means the probability of a particle having position x and momentum p at time t, knowing its initial probability. So you give initial conditions that are distributed in some way, and this fixes the initial probability. So when t is equal to 0, you know this object, and then you want to know how this object evolves in time, and eventually where does it converge to. The Kramer's name is applied to the case where you remain in the underdamped formulation where you have the velocity and the moment and the position, both of them. While when you work in the overdamped limit, where you drop the dependence on the momentum, as I was describing yesterday, and just x, then you use the name Fokker-Planck. Okay, so this is more or less a nomenclature that I like to use and that you will find in the literature, not always, but kind of the majority rule, say, for the use of the names of these equations. So in a sketch, what I'm telling you here is that imagine that you start your positions, just look at the overdamped limit. So you start the positions at a given position x of 0. This is time 0. So you start all the trajectories at the same position and you let them evolve. So as you know, due to the noise, these trajectories will be a little bit random like this. And imagine that you look at a given time t and you want to know what is the probability density of the positions at that time t. So you can say probability density between t and dt. What is the probability density of having positions around the initial value, but distributed in some way? So you can eventually, if you do, run your Langevin equations many times, and you do histograms, you can read this px of t from those trajectories. So this is a very bad sketch, but okay, a sketch of the joint PDF of the position and the momentum at a given time t will be some probability form around x0, typically for the initial for the position, because okay, the trajectory is spread around the initial value, and for p, typically, as we saw yesterday, the velocities decay towards 0. So on the other axis, this probability will go towards something that is around 0, is distributed around 0. So you have some kind of bell shape like this at a given time t after the initial one, and this will change in time, and you want to know how it changes in time. Of course, this is usually easier to visualize if you take the overdamped limit. So this kind of limit I was discussing yesterday, and then you have a function of a single variable that evolves in time. So for example, in the sketches I was showing you before, starting always from the same initial condition, I have a delta peak for the initial conditions around x0, and then in time, this distribution will evolve, will widen, and eventually will go somewhere. I don't know, maybe it will approach some limiting form, like could be, for example, this violet form over here. So the evolution in time is sketched in this way. So blue is initial, then later T1, later T2, and then perhaps it converges to something. And we typically are interested in knowing whether it converges to some limiting form and which is that limiting form. So the question is, how does one derive an equation for this p of p and x and t, if you are in the Kramer's case, knowing that these positions and momenta of the particle evolve through the Langevin equation? So the first thing to do in these cases is to think in terms of discretized time. So this is the continuous time axis, but now I discretize it. So I have increments of time, which I'm going to call delta t, and I have discrete times ck, which I index or label with a natural number k, that is 0, 1, 2, so on and so forth. So these are the discrete times which are sketched on this axis here. So if one wants to write the probability distribution at a subsequent time t plus delta t, so imagine that, I don't know, t is here, is number 3, and then you have t plus delta t, which is number 4. And if you want to write the probability distribution at these 4, so t plus delta t, you're going to try to write some iteration procedure, some expression that tells you how this probability evolved from the previous one. But if you have a problem which is not Markovian, this will not only depend on what happened in the previous time step, it will depend on the whole history of the process. Because remember, when I was showing you, for example, the correlations of the noise, they were depending on this gamma function that involved, that decayed in time the same way with time distances, but it was not something local in time. And the friction coefficient as well, it was not just a friction coefficient, it was a friction kernel going from 0 to the measuring time t that appears in the Langevin equation. So in general, if one wants to write some kind of evolution equation for the p at, I'm using the overdamped limit where no, well, here I forgot. No, actually, I'm using both. Here I forgot to write the t. So if I want to, evolve my probability distribution somehow, the whole history, it should be there. And I won't be able to do anything very useful with this, this expression is exact, but I don't know this one, I don't know that one, I don't know anyone, and I cannot write, simple expressions for any of the ingredients appearing in this right-hand side of my equation. So basically, one cannot do much with this, and one cannot write a useful equation for this probability distribution in non-Markovian cases. So one has to restrict to the Markovian cases, only for delta correlated noises and for local in time frictions. So in those cases, one can use a version of what sometimes is called the Chapman-Kolmogorov equation. It's just, composition of probabilities, basically. And in those cases, what happens in time t plus delta t will only be determined by what happened in t. So if you know what happened in t, then you can build what's going to happen in the next time step. And basically, this equation is an exact relation where what I'm doing here is I'm introducing a transition probability. I think that Fred used something like this also in his first lecture. So let me tell you what is here. Imagine that you know the probability distribution of your P naught and X naught. I'm going to call it P naught and X naught because they function like an initial condition in this equation. But these are the values that the position and the momentum take at the time t. They're not the initial values, of the Langevin process. But I'm calling them X naught, P naught, because I'm considering them fixed. I know them. I know where the particle was at time X naught and at time P naught. Sorry, at time t, at position P naught, X naught, and at momentum P naught. This one I know. And then I want to evolve it. So what I have to do is I have to say that how I have to evaluate, I have to try to find a way to know how this position and momentum evolves from these values to the next ones in the infinitesimal time step delta t that takes me from t to t plus delta t. And basically what I have to do is I have to consider all the possible initial values that I could have had at time t and integrate over them. And integrate over them with the condition of this transitioning from those X naught, P naught values to the ones I know I want to evaluate, I want to see. So in my little picture here, I think that Fred did something like this. Certainly used this kind of reasoning yesterday as well. Imagine that I want to know the probability of being at this point X here. Well, at this point X in my drawing, I came from this other point at the previous step, which is slightly below. But in another trajectory, I could have come from another point, which was coming from above, say something like that. I don't know. And then yet in another one, I could have come like this. So I have to consider all the possible ways of arriving at that point from the previous step t and going to that point I want to look at t plus delta t. Is it clear? And I have to integrate over all the possible positions and all the possible momenta that take me to that final, say, X and final P. So I insist upon this. I'm calling it is not P naught because it's like initial condition. And this is why I'm going to call this like this in the rest of this derivation. Okay, that's very nice, but I have to get some expression for this transition probability. And the form of this expression for the transition probability will depend on the kind of stochastic process you're working with. The previous relation between probabilities is completely general. It hasn't used Langevin processes. But now I'm going to use Langevin processes, Markovian Langevin processes, to evaluate this transition probability. And what I'm going to do is I'm going to enforce that the position that my Langevin process takes at time t plus delta t is given by the external value x I want to have, and that the momentum that the Langevin process has as t plus delta t has the momentum p that I want to have. And this I do by imposing two delta functions on x and on p, and I want to do it over, I want to average over all possible noises that can lead me to that final position and that final momentum. Just like in my previous drawing here, I said, okay, there are many, many noises that can take me from the previous values to the one I want. So I have to consider them all, and I have to average over each of them with their probability distribution, so the probability of the noise. This is what these angular brackets here are representing, an average over the noise. So this is what I'm stressing here. So this p and t and plus delta t, x at t plus delta t are imposed by the trajectory. And the trajectory depends on the noise. So these depend on the noise, though that depends on the noise. So I could have written more explicitly, if you wish, subscript psi to say that they depend on the noise. But they get there from some initial condition. And this initial condition is the value they had at the previous step. So it's this p naught and this x naught. Themselves are distributed, this p naught and this x naught, and the weight they have is given by this probability here. So, okay, so this is what I'm stressing here. And the noise that I have to consider is the noise that was drawn, the value of this random force, the noise that was drawn at the previous step t, the one that was leading me, that is going to lead me from position at t to position at t plus delta t and momentum at t and so to the one at delta t plus delta t. Okay, so this is the setting. Now I'm going to make some simplifications just to make the calculations easier. The first simplification I'm going to do is that I'm going to focus on the additive noise case. This can be generalized to multiplicative noise. It's not very difficult, but it would just make the expressions a little bit more complicated. So I don't want to bother you with that. If you're interested, I can give you references. There's no difficulty, a little bit more tricky, the multiplicative noise case, but it's possible. So there's no restriction to additive noise. It's just a simplification. And the other one is that I'm going to take the overdamp limits because it's easier to write and it's easier to do and so on and so forth. But generalization to overdamp is also okay and will lead you to the Cramer's equation that I will give you at the end. So there's no, again, these two simplifications are just simplifications. They're not restrictions. So if I just focus on the overdamp case, the updating equation, say, for P of x and t is this one. Just got rid of the p's, the momenta, and the transition probability just has one delta function, and I have to average over the noise, and we have to now evaluate this thing here. So to evaluate that, I have to use the Langevin equation, and I have to use the Langevin equation in its overdamped white noise non-memory form, which is this one. So this F is just some external force, whatever, and this is friction coefficient, velocity and noise. So we have to discretize it. And we have to discretize it, and we have to be a little bit careful when we discretize. There are some issues about discretization. So basically, what does it mean, the t, the x of t that is here? Is it really a t? Is it a t plus delta t? I don't want to enter into those problems here. They can be tricky to deal with in the multiplicative noise cases, not in the additive noise cases. So in the additive noise, I can just use what is called Ito discretization, which is the more natural one, if you wish. It's actually the more natural one that you use when you integrate numerically these equations, because you just say that what's going to be the next step is just given by what happened in the previous one, basically that. And if you discretize, this derivative here, okay, you have the value at the post time minus the value at the previous time, but I put it in the right-hand side of the equation, and some increment of delta x. And this increment delta x is determined by what's in the right-hand side of the equation. and I will write it in a second. But before doing that, notice that the x at time t is the initial condition for my infinitesimal evolution. So it's what I called x naught, right? So I just replace x of t by x naught. I still have the delta t here. And this delta t with this Ito discretization is just 1 over gamma, because I put the gamma on the right-hand side, f of x of t, but x of t, again, is x naught. So I write x naught. Multiplied by delta t, this delta t comes from the derivative. So, when I have the variation in delta x over the variation in delta t, I put it on the right-hand side. So here's the delta t. Plus what comes from the noise. So the noise times delta t over gamma as well. So this is just the most trivial discretization of this first order differential equation that you can think of, and is the one that, if you do numerical simulations, is the one that you use. Okay, now I have an expression of x of t plus delta t in terms of x naught and the noise. So I have to replace it here in the delta function that I had above to be average over the noise, you remember? So I have the delta function that imposes this condition on the position of the trajectory. I just replace by here x naught, and I write delta x instead of writing this full expression, but I keep in mind later that I know what is delta x. Now what I do is I expand this delta function, because delta x is supposed to be small, right? The increment in an infinitesimal time step will be small. So I suppose it's small, and I expand using this delta x small, just Taylor expand. So the first term is the delta of x minus x0. The second one has a derivative of the delta times delta x. And importantly enough, in these processes, one has to go one next order in delta x, because this will contribute to the final result. I cannot just drop it and stay first order in delta x. I had to go to delta x squared. Delta x squared, what is it? Well, it's the second derivative of the delta, 1/2 delta x squared. And then there are corrections which will be negligible, order delta x cubed. But this is very important. Now we put this within the average, and I take the average. So the first term doesn't depend on the noise. So the average is identical to itself. The second term, it has the delta prime of x minus x naught, but neither x naught nor x depend on the noise. So I can take it out of the average. What depends on the noise is the delta x. And this one I have to average. And the second order term, okay, the 1/2, the delta second, don't depend on the noise, because I remind you, x naught is my initial condition, is fixed. X is the value I want to evaluate, so it doesn't depend on the noise either, I chose it. What depends on the noise is delta x squared, so this one I have to average. And I have already dropped the correction. Now, what I can do is I can average delta x over the noise. The first term doesn't depend on the noise. It's a deterministic force evaluated at x naught, doesn't depend on the noise. The average is identical to itself. The second term makes appear the average of the noise, but the average of the noise, I chose it to be 0 at all times. It has 0 average, my noise. So this one is 0. So this average of delta x is very simple. It's just this expression. Now what happens with delta x squared? I have to take the expression for delta x squared and take the average. My first term will be basically the square of this. That doesn't depend on the noise, but it's there. But it's order delta t squared, right? Because it's squared, so delta t squared. For the moment, I keep it, but it's boxed because it will disappear soon. The second term is a term that will make appear the average of delta of the noise alone. So this one will be 0 because of the average of the noise being chosen to be 0. But then there is another term, which is the average of the noise squared at the same time, measured at the same time. So it has a delta t squared. So you could have thought it will be order delta t squared. So it will be order the same order as the first one. But it happens to be that it's not, because this thing here diverges like 1 over delta t. Why so? Well, why do I claim that this average is proportional to kBt times friction times 2 divided by delta t? Because remember that I have chosen Langevin has chosen the correlations of the white noise to be delta correlated, like a direct delta function. Now I'm discretizing time, and I have to discretize this delta function. So I have to make a representation of this delta function on discrete time such that it diverges at equal times, and its integral, when I go with an integration over it, so I go through it, gives me 1, right? Because I want the normalization of the delta function. I know that the integration over time of the delta function is 1. So I have to keep this condition as well. So there is a easy way to discretize a delta function over a discretized time over steps of delta t, and representing it discretized like this. I'm using this notation to represent the discretized delta function, which is 0 everywhere, apart from a little step here around the value where I'm evaluating this delta function, which is 0 in this case, of width delta t and of height 1 over delta t. So you see that if I take delta t, if I evaluate at 0, and I take delta t to 0, this diverges. So I have the divergence of my delta function. And if I integrate over this, I will pick through this step a weight of 1 over delta t times a width, which is delta t. So I get 1. Okay, so this is a good discretization. There can be others. This is not the only one, but it is a very simple one that gives you the two properties of a delta function. So that it diverges when delta t goes to 0, and that integrated over time, it gives you 1. So if now I have to evaluate this at equal times, this average of psi squared at equal times, I have to evaluate it as the discretized delta function at the value where it diverges. And it diverges as 1 over delta t. This is why there is this 1 over delta t here. And the prefactor on top is just the one that Langevin chose yesterday for the width of, for the weight, sorry, of these correlations that ensures, remember, that the velocity was converging to its equipartition expression. The averages of the square of the velocity was given by the equipartition rule with the temperature kBt. So this is what Langevin told me, this is what Langevin told me, and this is just the discretization of the delta function. So it turns out that this last term is order delta t, while this other term here is order delta t squared. So this is much smaller than this one. And actually, it turns out that this one can be neglected with respect to that one. This is already 0, so I don't care about that one. And this is the one that I have to keep from this contribution order delta t squared, delta x squared, sorry, average over the noise. So all in all, well, I repeat here a little bit. This is negligible. This is 0. Sorry, the other one was 0. This is order delta t, and higher order terms will also be negligible as the first one, so I just don't write them. So all in all, this average of delta x squared is given by a single term order delta t, linear in delta t, with this weight, and okay, then corrections order delta t. So now I put all this back into this transition probability, which was the average over the noise of the delta function. I replace, you know, I had this expression to order delta x squared. I replace where I have just evaluated for the delta x and the delta x squared. I replace here, I replace there, the two go. I insert this expression in my evolution equation for the probabilities. So I have this one, I replace, this is what I'm evaluating here, so I replace here. And now they're all delta functions, derivatives. This is just a single delta function. This is a derivative. This is second derivative. There, you see, this term is delta t, order delta t. That one is order delta t. This is order 1. I replace. So, I mean, I integrate. So this fixes the x naught to be x. This is the first term. All the other terms are proportional to 1 over gamma. So this is why there is 1 over gamma. This one here, I can integrate by parts, do the integration over the x. Or I can, if you wish, put the derivative outside of the integral because it's applying on the x, and the x is not the one which is integrated, so I put it outside. Then I fix my x naught to be x here, and in the end also here, and in the end I have this times delta t. And in the end, in the last one, I do the same. Actually, I take the two derivatives outside of the integral. I fix here p to be x. I have the prefactor, I have the delta t, and I have the second derivative with respect to x. Okay, and I should have written these as partial derivatives, actually, not total derivatives. So let me correct. Like this, because the function p depends on two variables, which are x and t, and here I'm taking partial derivatives with respect to x, not with respect to t. Okay, good. So I still have the equation written in terms of increments of the order delta t, but now very simply I can reorder, so I can move this p of x and t to the left-hand side. I can divide by delta t, I can multiply by little gamma. So you see that on the left-hand side, I have built a partial derivative with respect to time. So this is the left-hand side, and everything else remains on the right-hand side is just this term here and this other term here, which are those. Okay, so this is the Fokker-Planck equation. So this is Fokker-Planck equation, which is a partial differential equation, partial differential with respect to t, partial differential with respect to x, that acts on this probability density of being at position x at time t. And you see, it's a non-trivial equation, of course, but okay, it's a closed equation and it's local in time. This is very important. So this is local in time. It doesn't have memory. And it doesn't have memory because I have started from, a Langevin equation without memory. I cannot write down a simple equation like this for a problem which is non-Markovian. There's some approximations, some tricks in the literature, not so many actually, to write possible Fokker-Planck extensions for non-Markovian equations of Langevin kind, but none of them is very useful, I would say. Now, if you want to keep the velocities and the momenta, so you will basically do the same steps that I did with two equations, a set of two equations, one on momentum, one on positions, same tricks. You end up with an equation which looks like this. So this capital P now depends on momentum and position and time. It's also a partial differential equation. It has two kinds of terms. So it has terms which give you an evolution that you would also have without the coupling to the noise. So it's kind of a Hamiltonian flow equation that you have here, because you're now doing like real classical mechanics. You can do like real classical mechanics in phase space. And then you have terms which do depend on gamma, the friction coefficient, and that tell you about the dissipative part of the evolution. It's not difficult to derive this other equation. But I insist on the fact that both cases hold only for Markovian processes. And if color noise, there is no local in time differential equation like this that can be derived. This is very important. Now, okay, these equations are approximate. Let's see where I am. These equations are approximate, are restrictive in the sense that they apply to certain classes of stochastic processes only. They are exact for those. Those exist in nature, so there are cases where you can assume that noise is Markovian. So for those cases, they are very useful because there's a certain number of calculations which are easier to do within the Fokker-Planck formulation or Kramer's formulation than within the Langevin formulation. So when the two formalisms are good enough, you can choose, either you use one or you use the other one. When color noise is important, you have to stick for the moment to the Langevin processes. Okay, extensions to multiplicative white noise are okay, they can be done, but then discretization issues are a little bit more tricky. Okay, if you're interested, we can discuss it. I can give you references. I will not do it here. It has to be done carefully. Once you do it carefully, you derive a Fokker-Planck or Kramer's equation for those as well, but you have to be a little bit careful there. And what is this formulation useful for? As I said already, some calculations are easier to do this way. And in particular, something which is easier to do this way is to prove that your Langevin process, equivalent to your Fokker-Planck or Cramer's process, does take you, or when do those processes take the system to equilibrium? So when are you sure that if you wait long enough, your system will eventually reach Boltzmann equilibration with, the Maxwell term for the kinetic energy and the potential term for the potential energy? So using this Fokker-Planck formulation, or even the Cramer's one, it is very easy to prove that the Cramer's equation or the Fokker-Planck equation admit a solution which is stationary, meaning that it doesn't depend on time. So the partial time derivative of P is equal to 0. So you impose it. So you impose it on the left-hand side. So you set this left-hand side to 0. You're left with something here. And if in this something here, F derives from a potential, so if this F is minus the derivative of a potential energy with respect to X, then all this right-hand side is cancelled. It is equal to 0, setting this big P equal to your Boltzmann distribution. So let me write it. Oh, here it is. So this expression for P, which is the Maxwell-Boltzmann distribution, where you have e to the minus beta, the h of the system, and the h of the system is made by the kinetic energy, which is a function of P, plus the potential energy, which is a function of X. So this expression cancels, sets to 0, this right-hand side here. So actually it sets to 0 separately this Hamiltonian flow and this dissipated part. And this is valid for any value of gamma. So gamma doesn't appear in this asymptotic, in this stationary solution, but KBT does. KBT does appear because to cancel these two terms in the exponential, you need to use a beta here, which is 1 over KBT. So we can show, using this Cramer's or Fokker-Planck equation, that for these cases, there is a stationary solution which is of equilibrium kind, canonical equilibrium kind. Of course, you don't prove like this, just by setting this left-hand side to 0, you don't prove that your evolution will take you there. Maybe there is another solution that is not this one. This you don't know unless you solve this equation, this stationary condition for any possible, you find any possible solution to that stationary solution. So there could be, for certain problems, I don't know, there could be steady states which are different from the Boltzmann one. Or there could be situations where the time needed to reach this asymptotic solution becomes so large, like in the cases that Fred was discussing this morning in classes, the equilibration time becomes so huge that in practice you don't get here. In practice, this P of X and P is always evolving in time, very slowly, so slowly that it doesn't manage to get here. Okay? So there are other ways which are very beautiful to analyze what happens with this equation if you want to understand how and in which cases the solution to these equations do really approach this Maxwell-Boltzmann asymptotic form, and try to estimate what is the time needed to do it. And just to let you know, this is one way of looking at that is going through a mapping of these kind of equations to Schrödinger-like equations, and working with the spectrum of that Schrödinger-like equation and seeing, how this spectrum closes depending on how many degrees of freedom typically you have in your problem. Okay, I don't want to discuss that, but it's very nicely discussed, for example, in Paris's statistical physics book. So what is important to stress here, what I want to stress here is that there is a stationary solution which is of Gibbs-Boltzmann kind for those evolutions. So this is proving you that the Langevin process that I or that Langevin proposed, and that I was discussing yesterday, is able to take the system to equilibrium. It can take super long. It can be, unreachable in practice in your lab. But if there is a kinetic energy of normal kind and a potential energy of normal kind as well, so this I have to stress as well, a potential energy that is confining, so that it goes to infinity at infinity. So it doesn't allow your particle to diverge to infinity. It really confines your particle to a finite region of space. Then this probability exists as an asymptotic value, as an stationary value, sorry, of the full Cramer's equation. And why do you need this V of x to go to infinity at infinity and confine the particle? Because otherwise, basically, this measure wouldn't be normalizable. So to have a z of beta, which is the partition function, which is basically the integral over phase space of what is on the numerator here, it has to be finite. It has to exist. And for that to exist, you need V to be confining. So it has to have hard walls somewhere, or a potential that confines the particle and doesn't allow it to go to infinity. But okay, this is a detail. It's important in certain contexts, and I will discuss it more a little bit later. But in normal situations where you have normal kinetic energy, normal potential energy, then you have this possibility of having this stationary solution. If you wanted to prove that the Langevin process from the formulation I was using yesterday does take to this Gibbs-Boltzmann-Maxwell distribution, it's more difficult to do it from the stochastic process itself. But from the Markovian Fokker-Planck or Cramer's equation, it's relatively easy. At least it's easy to prove that it's a stationary solution, as I insisted. So I said already, confining potential, noise in equilibrium, because if I were to work with the case in which the friction and the noise were not balanced, obeying Ditten balance, as Fred was expressing this morning, then I maybe are able to derive some equation that rules the evolution of a probability distribution, but it will not have this distribution as a stationary solution. Okay. Now, all this I'm discussing now doesn't apply to color noise, but if I use Langevin processes with balanced color noise, those also take my system to equilibrium. I cannot prove it this way, but I will be able to prove it in a different way, which goes through those generating functions that I was mentioning later on. But just to insist upon this here, even for the balanced color noise, those processes take the system to equilibration, but the equilibration time can be huge. And in particular, it could be a function of system size. And if it is a function of system size, like the case of the glasses that Fred was discussing this morning, those equilibration times exist. For finite system sizes, they are finite. But the problem is that they grow so fast with system size that you cannot go beyond them in an experiment, or even sometimes in numerical simulations. And then you're stuck with having to deal with out of equilibrium dynamics and non-trivial evolutions of these probability distributions and those trajectories that lead to that. And you have to try to understand the out of equilibrium phenomena. And this is not just detail, it's the physics of the problems. The physics of the problems are such that those systems evolve in practice, in real life, too slowly to be describable by equilibrium distributions, and one has to forget about this and do just dynamics and look at the dynamics. Other questions here, because this is a good place to stop for a second and ask for questions if you have. Yes.
So this be sure. This is one solution.
This is one solution.
But you may have many. So if you really want to know if this is theory, so that's what that will be one way to do it.
To prove that there is only one solution.
For your particular system.
Okay, so if you do the Fokker-Planck mapping to the Schrödinger, and then you study the spectrum of the Schrödinger, you can prove that for that particular energy that you have in this Schrödinger equation, there is a single ground state. And then you're sure that this is your actual unique stationary solution. But there could be other problems where, B is very strange, or the force is very strange. We can go, because I haven't used to derive the Fokker Planck equation, I haven't said anything about the force. Then to say that I have this stationary Boltzmann distribution, I have to use that the force is the derivative of it. But if I forget about that and I use a generic force, I may have other steady state solutions to this Fokker Planck equation. Right?
So that's
That
why-
are not equal.
So that's to say that the first line in your Fokker Planck equation is not the real equation unless you have F coming from a potential.
Exactly. That's right. But the mapping to the Schrödinger is super beautiful, and then you look at the spectrum and so on. But for that, you have to use that the force is the derivative of a potential. Otherwise, it doesn't work. There was another, yeah.
Is there always an
Yes, because if I set to 0, well, if F is equal to minus B prime, right? If the force is equal to the derivative of the potential, then it's very easy to prove that this expression I wrote sets to 0 the right hand side of the thing. If you select an arbitrary force, it may not have a stationary solution. Yeah. Yes.
Transition might drop the term of the delta of B derivation of the
Let me see. Which one did I drop? Here? No. Below?
yeah, you drop the delta of P minus B.
Sorry, I didn't understand. Yeah.
There you drop the delta of P, in the expectation bubble.
Yes.
In the first line.
In the first line, yes.
Yeah, you drop the delta of B minus B. I didn't understand why.
This is just the Taylor expansion of the delta function. So what did I do wrong? Why I'm not using P the momentum, you mean?
There's no wrong.
Here I'm just using the overdamp, exactly. And in these slides, I focus on the overdamp case to make my expression shorter, basically. Not to write, because it gets very long if I have to write the T and the X. I'm just focusing on the overdamp case, where there is no momentum. But you can follow the same lines and just add another equation that relates T to X, and then impose the two delta, right?
The Cramer.
And then you do the Cramer, and then you change the Cramer equation, following the same step. There's nothing very difficult. You're welcome. Okay, now what I'm going to do is I'm going to tell you a little bit about quantum. This actually I'm going to do it because my seminar will be about quantum. So I thought that it was going to be a little bit useful to introduce you without doing all the calculations because these are really long. But I can give you references and I can even give you my lecture notes because I teach it in your course, Fred. I teach it in the, the master that Fred organizes. So what this Lindblad equation is, which was very mysterious to me until I learned it to teach it, is an equation that people use in the quantum world, basically in quantum optics, a little bit people who do atomic physics, not so much so in condensed matter, but a little bit as well. It's, to me, it's the equivalent of the Fokker-Planck equation of the classical problem written for the quantum problem. So there are a long number of assumptions which are made to derive this Lindblad equation that I will tell you about. And Markovianity is very, very important. Separation of timescales in the way I used it yesterday when I was working with the Langevin equation and telling you that the noise was much faster that, the environment was much faster than the system. Those are the more important ones that people use in this context. So let me remind you a little bit of quantum mechanics. So imagine that you have a quantum system in a mixed state. So this is not, just a pure state, it's a mixed state that you don't know very well. And the fact that you don't know very well, you represent it through a density operator. This is a standard quantum formulation, let's say, where you're mixing different states, which are the basis of your Hilbert space, the one that you like, depending on your problem. You choose a basis of the Hilbert space, and you weight those states with some probabilities. So these p alphas are real numbers, they're probabilities, they add up to 1. And this bracket notation is telling you that this rho hat is an operator. And this rho hat, I don't know if you remember quantum mechanics, but it's telling you about the state of the system, but not in a pure state version, but in a mixed one that you don't know very well. So the fact that you don't know it very well is due or is represented by the fact that you have these probabilities here that weight the different elements of the basis of your Hilbert space. So this could be, I don't know, eigenstates of the energy operator, or it could be something else, depending on the problem that you have at hand. So this rho hat is an operator. And if you remember quantum mechanics, an operator follows Heisenberg's equation, and this is Heisenberg's equation, right? So the time derivative of this rho hat, which will depend on time, it will evolve, in your system is ruled by the commutator of the Hamiltonian of your system and the rho itself. And there is an I and H bar. So if the system is isolated, or closed system like the ones I was discussing at the beginning yesterday in the talk, this is it. I mean, this gives you the evolution of this rho hat, and if you solve this, knowing the H, well, you know the evolution of your system in time. And I'm going to work with the H's, which are time independent. So my Hamiltonian of my system doesn't depend on time. So if this, if the system is isolated from the rest of the world, this is it. You have to solve this, and you get all your evolution of rho hat. And with the rho hat of time t, you can measure any observable. So you can take the trace of your observable times the rho hat, and this will give you the expectation of your observable, and that tells you about how the system behaves. But now I want to do something like what I did yesterday. So I want to consider that my system is open. I want to focus on a part of it, which I'm going to call the system, another part, which I'm going to call the bath, another part, which I'm going to call the coupling, the interaction, like yesterday. Now, exactly like yesterday, I have to model the bath and I have to model the coupling. And what people do, of course, is to try to model the bath in a simple way and try to model the coupling in a simple way, so that one can, as yesterday, get rid of the operators that consist of the bath, that make the bath, and get some expression for what is called the reduced density operator of the system, which is just defined as the trace of the whole density operator over the operators, over the elements of the bath. So say that, like yesterday, I had oscillators for my bath. Now I have a quantum object. So, okay, let me call B hat A, all the operators that characterize my bath. Could be oscillators, could be spins, could be electrons, I don't know, could be something else. I just call them B generically. So the idea is that you will integrate away all these B's from rho hat and get a reduced density operator for the system and try to derive an evolution equation for this reduced density operator of the system. So to me, this Lindblad equation that we will derive, which is the evolution equation of this rho reduced, is kind of a mixture between what we did yesterday for the Langevin process and what we did today for the Fokker-Planck. Because to me, the rho hat is a little bit like the P, the probability distribution, and still we'll derive this equation from the formalism of yesterday's, from the coupling between the system and the bath. So it's a little bit of a mix. And as I said, there are a number of approximations which are made on the way, which resemble the ones that we did yesterday. So under similar assumptions to the ones of the Langevin equations derivation. So basically assume that the coupling between the system and the bath is switched on at some initial time. Assume that the bath has a much faster decay dynamics than the system, that it's much larger than the system, and that is not modified by the system itself. So the coupling doesn't modify the bath, and a huge Markovian approximation. So I don't go through the details. The calculations are long, so I will not go, will not do it, but I will give you the references if you wish. So basically, one derives this Lindblad equation, which has a first line, which is identical to the previous one that I wrote for the evolution of the density operator for the whole system. So it's the time derivative of the rho of the system, there is the commutator, but here there is only the commutator of the system that appears. If I had to go back and, at the beginning, the h, which was here, is the whole h, is the sum of the three terms. So now here, there is just the one of the system that remains. And there are some other terms that arise from the coupling to the bath, which normally, and there are a number of assumptions, Markovianity, and loads of things, boil down to a sum over operators, that operators which represent what was the bath, and the rho density, and the rho deduce of the system. So don't pay much attention to this, but there is some extra term here that is representing how the system was coupled to the bath, and is summarized in these two kinds of terms. So there is an anti-commutator of these operators with the rho of the system, and there is this kind of a combination of the operators of the bath acting on the system, on the rho of the system. So as I said, there are a long number of steps that will bring you from the original Heisenberg equation on the rho hat here to this one that I wrote down there, and there is something that is linked to this counter term that we were discussing yesterday that also appears in this context, and that people treat in the similar way. Either they put the counter term and they kill it, or they don't put it and it's there. And if it's there, there is another term that appears here, which I didn't write, but it's appearing over there. So this is the starting point for many analyses in quantum many-body physics, because what people do is that in real situations, it's very difficult to derive what are these L's. So the L's here are some abstract operators that represent, what the bath is doing on the system, but you cannot derive them in an exact way. Similarly to what Fred was doing this morning. If you want to treat a system in finite dimensions, in interaction, many-body, and so on, you cannot do exact calculations. So what people do, and what I'm going to do in my seminar, is just to, in practice, choose these LMs. You choose them. You keep this structure, you choose the LNs, and you plug them in here, and you choose these coefficients. These are complex numbers. You choose them, and then you work with that equation. And typically, you choose a few of them. This sum is not a huge one. It's one term, two terms, depending on what you want to do. So there is a long derivation of this equation through a number of assumptions. You can have a look at it from the review article by Marco Schirò and Saro Fazio, which is in SciPost. There is another nice review article by Jamir Marino and other collaborators, 2025, and there is a book by Petrucciani and Bauer, I think, which is very nice as well, where you can see, the steps that, and you can follow my notes, but they're taken from theirs, so it's nothing very special. So this equation, as I said, there were huge steps taken in its derivation. It has some problems, huge problems, actually, I would say, but people tend to don't care about it. Anyway, so the big problem I think it has is that it doesn't have this as a, I should have said instead of asymptotic, maybe I should have said stationary. It doesn't have, the Boltzmann weight for the rho hat as a stationary solution, which is a bit of a strange thing, no? Because you write an evolution equation for the density operator of your system, and it doesn't go to, the Boltzmann one. But okay. If you're interested in out of equilibrium situations, well, you don't care about that and you use it anyhow. So, okay, this is one problem. Another problem is that it's local in time, just like the Fokker-Planck or the Kramers. There is no memory. And very often in quantum situations, the relaxation time of the bath is comparable to the one of the system you want to study. So you cannot do this separation of time scales and just, argue for Markovianity. You lose the physics of the problem by doing so. So it's similar to Kramers Fokker-Planck. It has this problem, but in certain situations, it's good enough and people use it. So still, okay for quantum optics. It can give a lot of ideas of how the systems behave. And I will use it in my seminar to argue for simple models of quantum active particles. So we will talk more about activity, Fred in his lecture this afternoon, and maybe myself tomorrow, or at least in the seminar. So how to let your system eat energy from the environment and use it to displace faster than it would do otherwise, and have some certain special properties. So there's a lot of people who are trying to do this in the quantum milieu. And so together with Marco Sarofazio and Marcos Quiroz, PhD student and postdoc, well, we have some proposal for some models of active quantum particles, which have their classical counterparts. So they're very simple, and they start from the Lindblad equation. So this is why I wanted to introduce the Lindblad equation, even though not proving it because it would be too long, but just keep in mind this kind of formulation. And keep in mind that it's approximate. Doesn't represent the full reality of these systems. Okay, so if I'm not mistaken, I talked for an hour, right? Have I talked for an hour? Yeah, okay, so let me stop here. I don't know if you have questions about the Lindblad, although, okay, it's a little bit quick. Yeah.
What is the stationary state of the Lindblad display?
It depends on the L's that you use, so it can be anything. So it's a bit worried.
And how do you choose the L's in general?
By hand. So, no, okay, you know a little bit about what's your bath. So you know a little bit which kind of operators that thing should be. So for example, if I have a bath of spins, it will be spin operators of some kind. And some functions of those spin operators. If you have, I don't know, a bath of oscillators, it would be, creation and destruction oscillator operators typically. So people who are, users of Lindblad, like Marco and Saro, they have a big experience, and very quickly, they say, okay, we have to use this operator, the other operator. But to me, it's a little bit of cooking magic.
Does anyone try to connect this with eigenstate thermalization? I mean, it feels like there should be some sort of...
Well, but eigenstate thermalization is for isolated problems, right? Well, this is, here you really want to describe the coupling to a bath, and you do it in a simplified way. So.
Yeah, but you think that eigenstate thermalization of the joint system, your H with no subscripts, should somehow imply something about thermalization in the Lindblad subsystem.
That could be. Yeah, that could be. Yeah, I don't know. Yeah.
Thank you.
I'm not such an expert in Lindblad. I actually learned it last year for the lectures, and I use it now with them. So I have two experiences with it.
Okay, so I have to one is regarding this question. So as far as I understand, but I might be wrong, these Lindblad equations, most of the time they only have one. That's what I was asking in the Fokker-Planck case, because in this case you always, I mean, it's very strange not to have just a single stationary state.
Yes.
And so therefore I was asking, because what I just learned from you is that the Fokker-Planck equation, you have many. I mean, you can have many.
If you have strange forces, right? Yeah. If you can, what I just meant is that typically one uses Fokker-Planck equations for equilibrium problems with a force which derives from a potential. But there are problems where you have, I don't know, you can have currents, or you can have forces that depend on time that you want to use, and in those cases you can have other kinds of steady states.
Okay.
Yeah.
And therefore, then the other comment is something I want to hear from you is. So you just mentioned something that I found very particular, I mean, attractive, because I also have noticed is that to the right, this one, the Limblad equation, you have a mix of the two
Yes.
cases. I was wondering, and maybe you have the same feeling, is that in this case, you're working at the same time with the state of the system, which is the position and momentum, you usually put it in the Langevin equations.
Right.
And then for the Fokker-Planck, you have the distribution of this stuff. While here, the rho is the same, it's the two things at the same time.
Absolutely, yeah. I fully agree. And it's a bit mysterious, no?
Mhm.
But it's surprising at least, I don't know. It's when you look at it at the first time, the derivation, when I looked at it, I said, okay, this is the same I do in many ways, the same I always do when I derive the Langevin equation by integrating away the oscillators and so on. But it's applied to a different object, no? So a different level of description in a sense. So yeah.
And finally, I usually teach this stuff. And then there is one step here that I was hoping to you, I mean, that you mentioned it just to have a different opinion on that. And it's that you have to do this, what is called the, I have it here because I always forget it, the secular approximation.
Yes.
To get this step, which you don't have in the classical case.
Sure.
So I just wanted to know if you have thought about it. And,
Yeah,
and
I have thought about it, and I
have.
didn't find anything interesting to say. Yes, yeah. It's I agree with you. It's a little. It's one more step, but maybe it's this one more step that makes everything Markovian, no? Because then you get rid of any kind of memory there. So it's related to the fact that we are working with both descriptions at the same time. So you don't need to do any secular approximation on the Langevin level, but you do something similar in the Fokker-Planck because you restrict to Markovian, and here as well. So, but yeah, I mean, I think there are many things that should be better studied from this Limblad formulation, and that maybe quantum people don't care because, okay, they just use it and that's it. But we have the other vision, no? The classical way of thinking that perhaps, you know, something nice can come up from a better study. But as I said, I'm new to the field, so yeah. I just remember that I always said that I didn't like the Limblad equation because it was local, and I knew that you know, in quantum physics you always have these delayed kernels that are important, Feynman-Vernon, that I will do later, and so on. And I was telling this to Camille, a former student of mine that Fred knows very well, and then he said, "But you know, the Limblad equation doesn't take to equilibrium, so it's really very strange." And then we discussed it a little bit. I said, "Oh yeah, this is really very weird." So, yeah. Yes, sure.
Yes, so I have a question precisely with the fact that you don't have any guarantee that it goes to the Boltzmann distribution. I suppose that will depend on the choice of the L.
No, I think that for me,
because
I think
it
that's
just seems to that the last part of the equation gives 0 for the.
I think that I mean, I'm not so sure. I may be saying something wrong, but I think that there's no choice of L's that takes you to equilibrium. There's a, you know.
But maybe if that.
But you have done so many assumptions on the way to write it this way, to write it in these you know, peculiar kind of combinations.
Because I was thinking just if you find some L that the last part of the equation, when you put the Boltzmann distribution gives 0,
yeah,
that would work.
Yes, you know that I agree.
But you don't know if there could be other solution, and you don't know where the system will.
Exactly, but I don't want to, you know, expand more about this because I don't know. So okay. Yeah, so I agree with you that the first part, if you put anything that depends on the age of the system, will be 0 because it commutes. So in particular the exponential form. But the second part is not so obvious, you know, what's going on with the second part. Yeah.
This thought, it seems like you would have something much more Fokker-Planck like if you had something that acted on the like Wigner function, you know, the phase-space distribution version. Do you know if this exists?
Yes, I think it exists. Yes, it does. Yes. Yeah.
Great.
Yeah, there are a couple of books which are nice. There is the Weiss book. from the 2000s, more or less. And there is another one which is Bauer and Petrucciani, no? Yeah. I think it's written this way, which are open quantum systems, and they're both very, very nice books.
Okay, another comment or question? No? We thank Leticia for this second session of the tutorial course.
I think I have a little bit more time, no?
10
10 minutes. I think I do.
Okay.
Yeah, yeah. Let me
Okay,
flash the last
so
part.
only a break.
It was good that I had questions, you know. That's very nice. So let me just very, very quickly flash for the students who probably don't know another formulation. So there's basically three ways of treating these problems that we use depending on convenience. And is the one in which we build a generating functional. So this is like a path integral, a classical one, like a Wiener path integral. So Feynman didn't know about Wiener apparently when he built his, but the way of doing both constructions is very, very similar. So here, again, we work on discretized time. We have an X that depends on the noise that follows the Langevin equation. And we want to compute observables, so averages over the noise of functions of that X of psi, and you can keep the momentum as well, but I'm not doing it to simplify the notation. So what this means is that you have to average over all possible noises, weighted with their probability distribution, the capital P, here, the function that you want to calculate. So each realization of the noise is, you know, all the xi's that were taken from the probability distribution at all these individual time steps, weighted with the probability distribution. And the probability distribution, we were always using Gaussian. Somebody asked me after the talk yesterday whether it was possible to have noises which are not Gaussian, and yes, it is. It's more difficult to work with them, but we typically just keep Gaussians because they are the ones who allow us to make calculations easy. So what this means, this object here, which is this path integral to start with, it's a product over all the little time steps of the noises, of the differentials of the noises at those time steps, of the Gaussian weight, this P over here, that could be colored. There's no problem here in the construction I want to sketch to work with the color noise. So it has the 1 over kBt here. Perhaps there is some factor, a numerical factor, which I'm forgetting. But what I want to stress is that there is a sum over all those time steps of the noises evaluated at the different time steps with a kernel, which is as the inverse of the other one, that these sums run over all the times. So the L's run from time 0 to the final time you may be interested in, and L prime as well. So this is a discretized Gaussian weight, and this is a discretized integration measure that I'm writing here. And this is what this curly D and this big P represent in this notation. So what you want to do is to write down a generating functional. So write down something that depends on what is called a source, lambda of T, that depends on time, and that by taking variations of this object with respect to the source, you make functions of psi go down from the exponential and average whatever you want to average. So for example, if you want to average psi, just psi, you take one derivative of these with respect to lambda, you make the integral come down, and you normalize. So this is basically what you do with a generating function. Okay. So the trick, what is the trick to, instead of working with what I wrote, make it useful, make it easier to work with? The trick, I will not explain it because of lack of time as well, but the idea is that you transform that integral over there into a path integral over the positions of your actual particle and auxiliary variables, which notation is used such that you put an I and you put an X hat. I mean, this is just notation. So these are auxiliary variables. So I will sketch it very briefly how you do that, but just let me tell you what you end up with. You end up with rewriting what I wrote above in the way of an integral over all the possible x's. I should have used the curly notation here. So an integral over all the possible x's and an integral over all the possible values of these auxiliary variables of something which is an exponential of an action that depends on those, on all the values that they can take on the time interval, and the part which has to do with the source. So this is kind of a trivial part. So the important point here is that you get rid of the noise. It's just an exact transformation. There are no tricks here, there are no approximations here. This is exact. You can rewrite what's above in this way, and you can obtain the exact expression for this action. And this you can do for multiplicative, colored noise, no approximations. It's only a little bit more difficult if you work with actually multiplicative white noise. And let me just sketch the hints, give hints on the steps. So you discretize time, you discretize the Langevin equation, as I did before. If inertia is present, there is no problems with using different prescriptions for the discretization. If overdamped and white noise, you have to be careful, but this can be done. What you do is that you impose the discretized Langevin equation with a delta function, like I did for the deriving the Fokker-Planck equation, but now you do at the level of these generating functions. And the delta you exponentiate, you Fourier transform the delta. You Fourier transform the delta with a wave vector, which is this x hat. Basically, the x hat is a wave vector that you're using in this Fourier transform. And once you have done this, you can integrate over the noise. You can get rid of the noise. And you end up with a form for this action, which is, okay, a little bit complicated, not so much so. It's an integral over time of x of t and I x hat of t. And although it can seem to be, much more complicated than the formulations I gave you before, for certain things, this formulation is better. In particular, this formulation is the one that people do in field theory, for example, perturbation theory, self-consistent approximations, and so on and so forth, are the ones, or evaluation of symmetries, identification of symmetries. Working with an action and a path integral is better suited for doing these kind of things. So this equivalent formulation is nice to do or to follow ideas or methods from other fields, from quantum field theory, for example. You can use it here, although it's classical. And something that you can do as well is what Feynman and Vernon did in the 60s, which is do exactly the same as what I did yesterday for the derivation of the Langevin equation. So you start with isolated problem where you have your system and you have your bath and you have the coupling. And for example, Feynman and Vernon said, let's model the bath with harmonic oscillators. So you integrate over, the particle variables, you integrate over the bath variables, and all these are curly Ds, sorry for the notation. You have the action of all of these, but then you integrate, you do the path integration over the oscillator variables. Okay, so they're just Gaussian integrals, those. You can do them. You can calculate them exactly. You integrate away the oscillator variables, which are these, and you end up with a new action, because it will modify this one. You end up with a new action, which has a piece which depends on the system, and a piece that Feynman and Vernon called the influence action. So the influence of the bath on the system, which depends on the variables of the system and depends on KBT and gamma. And I'm writing this with x and p. I could have written it with x and x hat. There is a transformation from x hat to p is the same. So p is like the x hat before. Don't worry about the change of the notation. So just to tell you that Feynman and Vernon did this calculation quantum mechanically, and they introduced this idea of the influence function. And this is just exactly the same as what Swansig and Mori and what's the other one, Kawasaki did in the classical field, most probably without knowing each other. But okay, the endpoint is the same. The formulation is a little bit different because they were doing path integrals for quantum. This is path integrals for classical. The other one was Langevin equations, but okay, it's the same. And just let me flash you one example. So this is the action that you get when you consider either you start from the Langevin equation with color noise, or you do the Feynman-Vernon procedure. So you end up with a piece which depends on the initial conditions. a piece which depends on here and there, just the Newtonian dynamics, and a piece which depends on the coupling to the bath. So this is coupling from the bath, this is coupling from the bath. So this comes from the integration over the noise, and this comes from the Langevin equation directly, but this, you see, depends on gamma, this depends on gamma, this is the influence of the noise, and the rest is just Newtonian dynamics. And this is initial conditions. And there's another term that, okay, it has to do with the discretization features. It's not very important, it's a Jacobian, has to do with that discretization, usually doesn't play a big role. So to end, let me tell you why this is useful. So this formalism is useful because it's exact. It can be written down for color noise as well, no problem. It can be written down for underdamped dynamics, also for overdamped. You can write down perturbation theory very easily here. You can do saddle point approximations, mean field approximations easily within this formulation. You can study symmetries, derive what in quantum is called world identities, but okay. From there, you can derive fluctuation dissipation relations, you can derive fluctuation theorems, you can do most of the stochastic thermodynamics calculations using this formulation, and it's relatively easy to do it this way. So I will end here. I have some more material, but okay, it's time to finish. I just wanted to show you a little bit the three ways of doing stochastic calculations. And tomorrow what I will do is I will tell you a little bit of phenomenology of, I will choose maybe glassy systems, maybe active, depending on what Fred will do this afternoon, and how these methods can be used to say something about the behavior of real many-body systems, complex, and so on. Thank you. If there are other questions, please. Yeah.
Questions, comments? No?
This Feynman approach is it's almost a derivation of Langevin, but there's not necessarily a unique way to then decouple the x hats, right? So presumably many Langevin equations could result in these same equations, no? Or is it not the case? Okay.
No, this one is for additive noise, no? If it were multiplicative, there would be this G factor somewhere. But for additive noise, I think this is the only one.
Wasn't this not for noise at all? Wasn't this for a system coupled to a bath?
This is, yeah.
Yeah, exactly.
So
it's a system coupled to a bath, right?
It comes to a bath.
Yeah, and then if you want to make this Langevin, you would have to then decouple the x hats.
If you want to read the Langevin from here.
Exactly.
Yes, yes.
But there's probably more than one way to decouple the x hats. That's the point.
Is there more than a way?
I don't know.
No, I'm not sure. I think there is only one. No, I don't think there are more than one. Yeah. No, it's this Hubbard-Stratonovich thing.
No, it's true. It's true. It's the one we use it as Gaussian.
It's Gaussian, exactly. Yeah. It's Gaussian. It's for Gaussian noise. If it were not Gaussian noise, yeah, I don't know. Yeah.
One last question or comment? No? So we can continue at 2 p.m. in the tutorial.
Thank you.